Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to talk about simplifying rational expressions. Now, this is the first lesson in my unit for rational functions, which is typically taught in Algebra 2 as a longer unit, but I kind of snuck it into my pre-calculus curriculum for my students because it is something that I feel like a lot of students need a lot of practice with. They see the fraction and immediately a lot of them freeze up. So that is what I'm going to work through in this kind of chapter. And for this first lesson, we're going to work on simplifying rational expressions by factoring, as well as applying the division property, applying operations, adding, subtracting, multiplying, dividing, looking at complex fractions, as well as excluded values. So the way I kind of started the lesson is I'm going to kind of work through obviously some problems with you. There are some problems though that I kind of did with all of my classes. So those are going to be kind of pre-inputted. So basically what I did is I kind of gave these prompts to my students and I just said, go ahead and simplify them. And let's just kind of see some of the mistakes you made. And students didn't always make the same mistakes that I would typically see them do. The one mistake I would see a lot, if these were kind of isolated problems, is they would want to divide out the twos. And we realize that if you divide out the twos, that gives you an answer of 3. But if you actually just apply the operation, you're going to get 5/2. So that is not the same. Dividing out the twos or just applying the operation is not the same. However, and when we have multiplication up in the numerator, when we divide out the twos or if we apply the operations, in both examples we get 3. So therefore, we can divide out the twos here, but we can't do it over here. Now, why is that the case? Well, basically the case is because in here, the 2 and the 3 are separated by addition, where here the 2 and 3 are separated by multiplication. So we can divide out terms when we have terms separated by multiplication, but not addition and subtraction. And so I did this again and again. A lot of students, again, now I just added some x's, but again, apply the operation and you can simplify. Here you can divide out the x's because the 5 in the x and the 2 in the x are separated by multiplication. Whereas you couldn't just divide out the 2x's, okay? Because you could see the answer is obviously not 3x. But over here, now that I have everything with multiplication, I can just go ahead and divide out, and that is equal to 3x. And then I worked my way one more time into expressions because typically students recognize, okay, yeah, I understand this portion and I can make this connection. But typically if I were to give them a problem like this isolated, a lot of students would want to divide out these x plus 2's. Or they would say you can't do this one because both these quantities, have addition in them. But again, the quantities can divide out what's inside the parentheses as long as they're separated by multiplication, which we have seen in, two examples here prior. So therefore, you don't need to multiply this operation and then divide the x plus 2. Nobody wants to do that, right? So therefore, we want to divide them out. Now, the understanding of dividing them out is what we call the division property. Because another thing actually I want to get through is a lot of people, confuse this with canceling out, right? And we use this word, and actually let me kind of go back to these, of terms cancel out. Well, they don't cancel out because we got to be very important. When something divides by itself, it equals 1. So in this case, actually, when I have 2x divided by 2x, actually 1 times 3x, right? Which just equals 3x. So it's very important for you to understand there is a 1 there. We just typically don't write it, but it's very going to be helpful for you to understand that the idea they divide to 1 instead of canceling out. And again, here we have, you can't divide out these terms. You can see addition separates these quantities, so therefore we can't divide them out there. A couple just things to, remember with the division property. Obviously, you're adding your terms, combining like terms, and they can go ahead and simplify. And again, I just kind of did these operations again as far as why the 2x's can't divide out, because that 2x is actually divided into both of those terms, which actually gives you an answer of 1 plus 3/2, which is 1 over 1 plus 3/2 actually, which is actually 2 over 2, so that's equal to actually 5/2, which we already knew from the original answer, right? Which is actually just the same kind of thing as distributive property. Okay, so then I talk with students about, we want to make sure we understand the division property, but again, that when things divide out, they equal 1, right? 2x over 2x equals 1. And again, I got this answer before, right? 5/2, yes, right? So obviously you wouldn't want to use all this work. You want to, make things easy on yourself, but I want you to see that you still get the 5/2. So then the next thing we want to talk about is the excluded values. And the excluded values is really a main Algebra 2 topic. I mean, in my class, we've already talked about holes, asymptotes, and the domain of excluded of when the denominator is equal to 0, of excluding those values. So that's basically why we first learn about excluded values, is values that just make the denominator 0. So the easy thing to understand is, just set the denominator equal to 0 and go ahead and solve. We're not going to be concerned if quantities divide out. Like in this case, you can see the x plus 1s divide out. For those of us that have already covered holes and asymptotes, we recognize that that is going to create, that is a removable discontinuity. And actually, I made that wrong. That's actually -1, isn't it? So -1 is a removable discontinuity, which is a hole, whereas 4 is a non-removable discontinuity, which also creates an asymptote. But for this case, we're just going to label excluded values any number that makes a denominator equal to 0. Okay, so really we're just going to practice simplifying. The main thing that, that students have a struggle with this is factoring. You got to factor the numerator and go ahead and factor the denominator and then just apply the division property. But it's really simple for what we did. So you can see I kind of gave them 2 examples here. Here's your original problem. The main idea that I told students to do is just factor, 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 factor. And obviously with trinomials, it's going to be rather simple. They can factor the numerator, factor the denominator. We see that the x minus 1s divide out. However, that doesn't mean the excluded value divides out, because 1 still makes my original denominator 0. So I just leave out the x minus 1 over, or x minus 2 over x minus 3. And therefore, x cannot equal 3 and 1. Those are going to be my excluded values. And you can see from those factors, obviously those are going to make each of those factors equal to 0. I did want to prepare students though, like, hey, we could also do some more difficult factoring problems, right? I could raise the powers now. I mean, this is, we don't have to just do easy trinomials. I could raise the power of the trinomial, or we could do factoring by grouping. So remember when we have polynomials to higher powers, and if it's a trinomial, just factor it like it's a quadratic, but then raise the power of the factors. And if you have a grouping problem, or if you have a polynomial with 4 terms, look to grouping, look to factor by grouping. So I did that, and I noticed that the quantities x squared plus 3 are going to divide out to 1. Leave me just with x squared plus 2 divided by 2x minus 3. Now this one's interesting. I only have one discontinuity here as our excluded value, which is 3/2. And the reason being is because x squared plus 3, which is my other quantity that is in the denominator, gives me an imaginary numbers. And we're not going to exclude imaginary numbers from there. We're only going to exclude real numbers that make our denominator equal to 0. So that's something we've already covered in this class as far as in our polynomials unit. So now what I like to do is just kind of work through 4 more examples with you. These are ones that I kind of gave through my class, and therefore we can just kind of, now work through these together. So there's really nothing else I can do in the numerator here. So that's just going to be left as x plus 3. However, in the denominator, basically I see that this is a quadratic trinomial. Thinking of what 2 numbers multiply to give me 3, add to give me 4. I'm thinking x plus 3 times x plus 1. Now, or I'm sorry, x plus, 1. Now again, guys, it doesn't always work this way, but it's a good idea. If you're simplifying a rational expression, something is going to divide out, right? So when you're factoring, if you get factors, most of the time, those same factors are going to be used in the numerator, right? Because you're going to be trying to divide things out. It's obviously not a rule. It has to occur. Like this could be an x minus 3, right? And then nothing would simplify. But why would we give a problem that says simplify if nothing divides out, okay? But anyways, you can see here the x plus 3s, they go ahead and divide out. When students did this though, a lot of them just put the x plus 1 in the numerator. But no, you got to think that x plus 1 is in the denominator. It's going to stay in the denominator, right? So then what do we put in the numerator? Well, obviously understanding the division property, x plus 3 divided by x plus 3, guys, gives us 1. So 1 is going to be in our numerator. Our excluded values, x cannot equal, is going to be -3 and -1. All right, next example, looks like we definitely have some LCD going on here. I can factor out a 4x. And that's going to leave me with a x minus 1. Here, I can factor out a 2 first. So that gives me an x squared plus 2x minus 3. Let's see, it looks like I can factor that again one more time. Let's just rewrite it here. So this becomes a 4x times x minus 1 all over a 2. Let's see, what two numbers multiply give me -3, add to give me a +2. That's going to be x plus 3 times x minus 1. Okay, again, we have our terms separated by multiplication, right? So my x minus 1s divide out. And then also notice I have a 4 and a 2, right? Well, again, since they're separated by multiplication, you know, each of their terms, then I can divide out that 4 and 2. Leave me with a 2. Like 4 over 2 just simplifies to 2, right? So that's going to leave me with a 2x over x plus 3. And again, let's just go ahead and label our excluded values here. Is going to be a -3 and a +1. Now, one mistake that students will make is they'll make the excluded value 2 because they see 2 in the denominator, or they'll say -2. But again, 2 or -2 does not make the denominator 0. The only two numbers that make the denominator 0 are -3, because that makes that quantity 0, and therefore everything is 0. And 1 makes this quantity 0. Therefore, when you multiply it by everything else, it's going to be 0. 2 is just a scalar, right? 2 is going to be a stretch or compression. And we remember that from polynomials. It's not actually going to impact our asymptotes, or, you know, anything that's going on the zeros of the graph, or at least our excluded values for right now. All right, next one, let's go ahead and simplify here. Again, I can factor out a 2. So I get an x squared minus 1. Here, I can't really factor anything out, but again, I noticed that my last term is 1. So it's either my factors, you know, I know that a trinomial, guys, is going to be a product of two factors, right? And they have to multiply to give me 2x and x. Now, the nice thing about this problem is a lot of people are like, I don't know how to factor when a is not equal to 1. Yeah, but look how easy this problem is. We know that we have to be a trinomial is going to be factored to the product of two binomials. We know we have to multiply to give us 2x squared. Now, the only two numbers that we can multiply to give us 1 are +1, and -1, -1. But since our middle terms have to combine to give us a +3x, my only options are going to be +1 and +1. So let's go ahead and do this. Hopefully you recognize that's a difference of two squares. Okay, and that's going to be over 2x plus 1 times x plus 1. You can now see the x plus 1's divide out, leave me with a final answer of 2x minus 2. Let's distribute this one. I'm perfectly fine with students if they don't distribute. 2x minus 2 and 2x plus 1. But in this case, let's go and distribute because it's not really that much work. But again, the reason why I want to distribute is, again, notice the 2's do not divide out. The x's do not divide out. And again, you could say, well, these are separated by multiplication. Yeah, but those quantities are also separated across those terms. So we can't be dividing out when you have other terms separated by that addition or subtraction. So therefore, that's going to be our final answer there. And then our excluded values is going to be -1/2 and -1. All right, last but not least here, we have this problem. So let's factor out a -x, right? Because whenever we factor, I like to have things in standard form. So I want, and also to be positive. So that's an x squared. Let's say that's going to be a -x plus 1 minus 2x. Shoot. Okay, so it's a minus 2x. Oh, I can't believe I did that. Minus 1. All right. And then over here, I'm going to rewrite this again in standard form. Actually, let's just rewrite it like this, -4 plus 1. And then I recognize I can't factor this, right? Unless I factor out again. Let's knock out this negative. So if I factor out a negative here, I'm getting x to the 4th minus 1. Now, you might not recognize, it's like, well, I don't know what else I can factor out. There's nothing else in common. But remember the difference of two squares. When you have x squared minus 1, that's x minus 1, x plus 1. This is a difference of two squares just raised to a higher power. So let's go and see what this is going to be simplified to. So therefore, let's do a -x times, this is going to be, that's not right. That should be a positive one. I knew something was going on. This is going to be an x minus 1. I'm going to write this out in factored form. Even you could write it as x minus 1 times x minus 1 squared. And then this I can write as x squared minus 1 times x squared plus 1. Now again, nothing divides out at this point, right? These are similar, but that's a squared and that's an x, so they're not exactly the same. However, what we recognize though is I can factor the x minus 1 or x squared minus 1 one more time, right? So that would be x minus 1 times x plus 1 times x squared plus 1. Now, obviously, you don't need to show as much work as I'm doing. I'm just kind of doing this, obviously, for a little bit of teaching material. A couple things we notice, though, is obviously negative divided by negative is just going to turn to a positive, right? The x minus 1 squared left divide out. We're going to be left with an x minus 1 in the numerator. So I'll just write that as a positive x, sorry. So that'd just be a positive x times x minus 1. And then in the denominator, I'm going to be left with a negative x plus 1 times an x squared plus 1. Now again, we don't need to consider the x squared plus 1 as a restricted value because again, if you were to set that equal to 0, you get negative 1 square root. That's going to be plus or minus I. So my restricted values here are only going to be from here, x cannot equal positive and negative 1. Okay? So there you go, ladies and gentlemen. That was just kind of the basics of simplifying, of having students factor and then divide out. And then we kind of went into adding and subtracting. So I went with students and said, all right, hopefully you guys remember adding and subtracting some basic fractions, from back in the day. And basically, I don't know, when you first learned how to add fractions, you remembered you had to find the common denominator. And so what I did is I just kind of went down memory lane, like how would you add and subtract fractions when they didn't have common denominators? Well, when we were first learning about denominator and multiples, what we do is we just list the multiples of each of our denominator. For instance, the multiples of 2, 2, 4, 6, 8, 10, 12. The multiples of 3, 3, 6, 9, 12, right? We just kind of listed them there. And then we just found the smallest one. You could have done 12, but we wanted to find the least common denominator. And then our goal is to obtain the common denominator, so therefore we could apply the operation addition or subtraction to the numerators. So basically we understood that 6 was the least common denominator. To get 6, I just multiplied by 3 over 3 on the left and 2 over 2. Remember, you had to do that to produce equivalent fractions, okay? And therefore, you can see that's how I got the 3 plus 2 is 5. Now, everything kind of gets thrown out the window once we include variables, because if you look at this, the multiples of 3 are simple, 3, 6, 9, 12, ... right? But once you start including x's, you could do 2x, 4x, 8x, you could do 2x squared, 2x cubed, 2x a fourth. There's like now infinite many. And even more importantly, they don't have anything in common, right? There's no factors that 3, 6, 9, and 12 have in common except for the number. Like they don't have any of the x's in common, right? Because these have no x's, these do. So then what can we do? How can we find the least common denominator? Well, one way, if you actually look at this, rather than listing these multiples, if you really, look at this, really the least common denominator of 6 is really just a product of the two denominators. And again, 3 and 2 do not have any factors in common, right? They have the smallest multiple they have in common is 6, but they don't have any factors in common. Factors, again, are numbers that divide into them. So they don't have any factors in common. So if you just multiply them, that will produce the least common denominator. So since 2x and 3x do not have anything in common, factors in common, I'm just going to multiply them to obtain 6x. Then I find my multipliers. That's going to produce my common denominator, which is 3 over 3 on the left side and 2x over 2x on the right side. And therefore, I can't really do anything with the numerators, right? They're not like terms, but you can apply the operation and go ahead and simplify it. And then we just kind of look at this one where it's like, all right, let's just keep on adding more x's, right? So now we're going to do some binomials, x plus 2, x plus 3. And a lot of people say, oh, but they have x's in common. Well, no, x is not a factor. Because again, if x was a factor, that means x would evenly divide into x plus 2. And sure, x divides into x, but it doesn't divide into x plus 2 evenly. If you remember long division, go ahead and try it. You're going to get a remainder. So therefore, they don't have any factors in common. So just using the same idea that we just practiced to find the LCD, we're just going to multiply them across. So x plus 2, x plus 3, we're not going to expand them. Let's just multiply them on the left, multiply on the right. And therefore, now we combine our like terms. And in this portion, I told my students to go ahead and just leave the denominator in factored form. Now, the only difference is you don't want to always get in the idea. You can do it of always just multiplying the denominators, but typically we're going to do some more advanced problems where you're not going to want to do that. That's not going to be the best way to go about that. So if we look at, a number with these fractions here, you can see that 6 and 2 have a common factor of 2, right? Because if I like break down 6 as 3 times 2, you can see that they share the 2. So now my LCD is going to be what they have in common, what factor they have in common, which in this case is a 2, times which factor they don't have in common, which in this case is 3. So 2 times 3 is 6. And you can see that obviously 6 divides into 6 and 2 divides into 6. So therefore that's why it's the LCD. You could multiply them to get a common denominator of 12, but again, as I mentioned, that's going to get more and more difficult to do once we get to more problems. The nice thing about only having a common denominator where you already have a denominator of that value is you only need to multiply the other side by 3 over 3 to go ahead and get your answer. So in this case, you can see they have the same thing. What do they have in common? They both have a factor of 2 in common and x in common. So they both share a 2 and the x, right, as factors, but they don't share a common factor of 3. So when I multiply by 3 over 3, I get 6x minus 6x, and now I can apply operations to the numerator. And then last but not least here for f, you can see that they share the quantity x plus 2 in common, right? So, here's x plus 6 times x plus 2. Here's just x plus 2. So since they share x plus 2, I'm going to include that in the LCD, multiply by the product of x plus 6. And then I multiply x plus 6 on the top and the bottom. Notice on this one, though, one really important thing that if you notice my work, I'm always using parentheses when I'm multiplying. Well, not always, but most of all. See, even like 3, I put parentheses. Most of the time, I'm always putting parentheses. 1, to remind myself that's multiplication, and then 2, to make sure that notice that this is not just a 1. This is actually a minus 1, right? So it's a negative 1, and you have to make sure you distribute that negative 1. You multiply that negative 1 to the x and to the positive 6. Because if you don't, then you're not applying distributive property, and therefore you're going to get the answer wrong. So it's really 1 minus x minus 6, and that's actually wrong. So it's negative x. And that I did the distributive property and actually did the math wrong. I'm glad I went and checked my answer. Oh, wait, no, I did it right. So, okay, I was saying that's what it's not equal to, right? So that's what most people do, is they won't distribute, and they'll just write it as, 1 minus x plus 6, and then they combine the 1 and the 6 to give you 7. But remember, as long as you distribute it, you're all right. Now, we do also do excluded values for these problems, but we'll get to that in our examples. So basically the process for adding and subtracting was to factor, simplify as necessary, obtain common denominators, and then apply the operation to the numerator, and then simplify if necessary. I think all these simple problems, there was no way to do that. But let's go ahead and look at the examples, though, and kind of see if we have some options there. All right, so for the choices I chose, we have add and subtract rational expressions and label the excluded values. So these are the two examples I kind of did in class. And in this case, you can see my denominators don't have anything in common. That's why the LCD is simply just the product of them, x times x plus 2. So I just multiplied by the other denominator, basically on the other side. Notice that I had to expand that, right, as a binomial times a binomial. And then I had to add that to 3x. So I actually expanded all that out. That gave me a negative 3x, but then you add that. And then I just combined my like terms in the numerator and went and factored out. Now, there's nothing really you can factor out here. I can't factor this numerator, so I'm just going to leave it as that. But it could be something to factor out either way. So that's always just something to check, look for. If it is factorable, then that's something you want to simplify one more time. But in this case, that wasn't the scenario. And then I just find the excluded values, which is basically the values that make my denominator equal to 0. Which is 0 and negative 1 in this case. Over here, a lot of people that, again, have trouble with this, they will go ahead and just multiply denominator times denominator because like, that's easy. I like doing that. But again, if you divide this out, what you recognize is they share the factor x minus 3. So therefore, the LCD is just going to be x minus 3 times x minus 2. So I don't need to do anything to the left side. All I need to do is multiply x minus 3 on the right-hand side, which actually makes your life a lot easier, right? So I multiply that on the right side. Make sure you keep that as a negative 4, and you distribute that. I got to check my work as well. Combine like terms, and you get a negative x plus 11. Nothing's going to divide out, and my excluded values were 3 and 2. So now let's go and work on some other examples that I did in class. So I guess I didn't give myself some work here. So hopefully I can all fit these in. All right, so the LCD in this case is going to be, they have nothing in common as far as factors go, right? They both have a 1 and an x, but they're not the same. So my LCD is going to be x plus 1, x minus 1. So therefore, to obtain that denominator, I'm just going to multiply by an x minus 1 over here and an x plus 1 over here. Okay, now you can see them going to be having the common denominator. And one thing I also want to point out too, I kind of did this. I wrote this out expanded, right? So you could do the left side, do the right side, and you can recognize once they have the common terms, like you're just combining them, right? You're just combining the numerators together under the same denominator. So I did this for instructional purposes for my students and for you, but to save myself time and space, I'm just going to multiply these and then put them under the same denominator because that's what's going to happen anyways. Just make sure you distribute here and you distribute here. So therefore, I'm going to have 3x minus 3 minus, let's see, that's going to be a 2x squared. And then again, remember, you're distributing the negative 2x plus 1, so that's going to be minus a 2x. And that's going to be all over x plus 1, x minus 1. Now you can write that. As a as x squared minus 1 if you like to, but I would tell my students, it's perfectly fine. You're just leaving it as you have it. So therefore, then I have a negative 2x squared. Let's see, plus x minus 3 all over, let's see, x plus 1 times x minus 1. Okay, so again, my excluded values is x cannot equal 1 and negative 1. I'm just going to factor out a negative and make sure that this is not factorable. 2x squared minus x plus 3. Just in case nothing would factor out, but I don't think I'm going to. I mean, it could be factorable, but I don't think anything's going to factor. I don't think any of my, that would have to be like a 3, and this would have to be a positive 1. No, that's not going to work, so it'd have to be a negative 1. 3x, and that'd be a positive x. Ooh, actually that works. X minus 1, yeah, that does work. Sweet. So you can see that becomes a 2x plus 3 times an x minus 1, right? And then you can see the x minus 1s actually would divide out. So let's actually hold those excluded values here. Okay, so going a little bit further, times x minus 1 divided by the x plus 1 times x minus 1. Those divide out, just leave me now with a negative 2x plus 3 over x plus 1, where x cannot equal plus or minus 1. Okay, so again, just want to make sure it doesn't always happen all the time, but we just want to make sure we clarify that nothing's going to divide out. And in this case, you can see that they actually divide out to give us that factored form. So we want to make sure we leave it in always our simplified, right? Because I believe the directions were to simplify them or add and subtract rational expressions. So I didn't really clarify simplifying, but if you're dealing with a multiple choice problem, you can see how that answer would have came about. All right, in the next example, they do not have anything in common, so I'm just going to multiply them. So that's x plus 3 times x minus 2. So I'll multiply these by x minus 2, multiply these by x plus 3. All right, and that's going to give us then a 2x squared minus 4x plus a 3x squared plus 9x all over my common factor of x plus 3 times x minus 2. And then I can simplify that. I can get this to be a 5x squared and then plus 5x. That gives me an x plus 3 times an x minus 2. Now, you could write this in factored form, right? You could factor out this numerator. It really kind of depends on what your teacher, wants from you. X plus 1, nothing's going to divide out. So when terms don't divide out, I just told my students, you can just leave it in factor or expanded form. Just make sure you understand that x cannot equal negative 3 and positive 2. So it was basically, as long as they had their excluded values and there was nothing that further got divided out, then I considered it to be in simplified form. All right, for B here, the issue here is, again, we say, oh, they don't have anything in common, multiply them. But again, it's like, well, let's factor out an x here. And when we factor out an x, we get an x minus 1. So therefore, we recognize here that they already have a quantity x minus 1 in common. The only thing we need over here is just another x, right? So that's actually rather easy. I just have an x squared plus a 3x squared over an x times x minus 1. Well, that problem's not too bad, right? That just gives you a 4x squared over x times x minus 1. However, you can see that an x can be divided out. So that's going to leave you with a 4x over x minus 1. And our restricted values, though, again, just because the x got divided out doesn't mean it doesn't go away. X can still not be 0 or 1. Because in the original problem, 0 and 1 would make my denominator 0. That's why they're excluded. The next one kind of gets a little tricky sometimes with people when they don't see another fraction. So again, I just told my students, write it as a fraction, right? So it's 3x over 1. Therefore, x plus 2 and 1, they need to, the only thing in common here is going to be x plus 2. So you're going to need to multiply by an x plus 2 here. And when doing that, I get 5 minus 3x squared minus 6x all over x plus 2. Let's go ahead and rearrange that and subtract out a x or a negative. See if that's going to be factorable. 3x squared plus 6x minus 5. And basically you want to see, is it going to be factorable with a 2, right? Is there going to be something that's going to divide out? So I know this is going to be 3x here and a 5. So therefore, if I need to get a positive negative 5, I can't multiply it. So two numbers give you 5 are going to be 5 and 1. I can't multiply 3 times 5. That's going to give me a 15. So then it has to be a 5 over here. And I'm not seeing anything that's going to be factorable, especially with the 2. There's nothing that's going to divide out with the 2. So that's going to be my simplified answer. And therefore x, oops, let's write that in there. Therefore, x cannot equal negative 2. And that was my only denominator, right? That was the only value that can make my denominator equal to 0. 1 was just in the denominator in that second fraction, but it doesn't actually make it 0. So really the main case for adding and subtracting rational functions or expressions is getting the common denominator, combining the numerators under the same denominator, and then go ahead and then from there, just make sure you look to simplify if you can. All right, then we worked into multiplication and division, and this was kind of like, a little bit of the same thing that we already did. So students kind of went through this a little bit quicker. The only thing that was kind of interesting though is, a lot of students, it brought back a lot of memories for like, how do you divide fractions? And one of the main things that I saw students doing was the keep, change, flip. And I'm not sure if you guys have ever learned it that way. But when they would divide something, if I had 6 divided by 1/2, they would keep the first term, change the operation from division to multiplication, and then they would flip the divisor, the 1/2, as the reciprocal. And they got 12, which is the correct answer. But the problem was I always asked them, like, why does that work? Like, why do we do keep, change, flip? Like, are you sure that's correct? And you sure that's always going to give you the right answer? And most of the students nobody could really explain the process. They just remembered it. So, which is great. I have no problem with, using some tools to remember some certain things. But I think it's really important to look at the division in a separate way so that we understand why keep, change, flips. And so what I showed them was, well, what if we wrote the fraction like this? 1/6 divided by 1/2. Well, again, my favorite fraction that I have is 6 over 1. Because 6 over 1 is just 6. So what that means is, if I have a fraction where 1 is in the denominator, I actually don't have a fraction. So right now, I have this big fraction. I have 1/6 over 1/2. Well, if I want to reduce this just to a single fraction, I need to get this number to be 1. So what should I multiply 1/2 by? Well, I need to multiply by its reciprocal, right? Because anything multiplied by its reciprocal is 1. And again, you just can't multiply the denominator by its reciprocal. You got to multiply the denominator and the numerator to keep an equivalent fraction. And when you do that, you obviously get 1 in the denominator and you get the keep, change, flip in the numerator. And that's why that works. And that's how you can go ahead and get your correct answer. So yeah, a couple other important things about multiplication as we get to it is, one thing, when we have something like multiplying, 1/2 times 6 over 2, you can multiply straight across. Like you can actually go through the operation of 1 times 6 is 6, 2 times 1 is 2, and then simplify it out, right? So you can apply the operation and then simplify. However, if I had 6 times 1/2, which I have in this case, a lot of times it's just better to understand that 2 divides into 6 3 times, right? So you could factor the 6. A lot of times we just do this in our head. We actually don't show it like this. But we can just factor things and then divide them out. We don't need to factor them, multiply them across, and then divide things out, right? So again, since our operation now is multiplication, we can apply the division property across multiplication. So that's what's kind of really important or helpful to understand now is you can apply the operation and then simplify. But to make our life easier and to make these problems easier, we're going to want to simplify them by factoring and apply the division property across multiplication. When it comes to our division problems, we're going to want to obviously rewrite them as multiplication. So basically for multiplication, we're just going to want to simplify each expression first. So simplify them and then apply the division property, right? Because we already have everything as multiplication. So therefore, you just apply the division property where you can. So, I only went through a couple examples in the class. For instance, here you can have 4 opportunities to factor, right? So you can see I went and factored everything. And then now, I don't have anything to divide my x minus 2 by, right? But again, this x minus 2 and this x minus 2, every single quantity is separated by multiplication, right? All these parentheses, these quantities in parentheses are separated by multiplication. So I just divided the x minus 2's across that. And therefore, you could see how that worked. You can see the 2 and the 4, everything is separated by multiplication. I know inside they're separated by addition and subtraction, right? That's why you can't divide, that's why you can't divide out these x's. But the quantities, you can go and divide across multiplication because the quantities are separated by multiplication. The important thing though too is also notice all these values that could be 0 in the denominators, -4, -1, and +2. Again, remember that 4 is just a scalar, right? So that's why that doesn't get divided out. And then go and simplify and then label excluded values. And that was really about it. So let's go ahead and get some factoring practice here and, just practice more factoring problems. That's really what I told students. It's not really a pre-calculus lesson in this case, but it's great practice for you as far as factoring. Uh-oh, what was that supposed to be? I think that's supposed to be a 1. Hopefully, it has to be a 1. All right. Let's go over here. So factor this. I know it's going to be a product of 2 binomials. 2x, I'm thinking this one's going to be 2, and that's going to be x, and that's going to be a +1. So I know since my last term is positive, my middle term is positive, both factors are going to be positive. I need to get 4x plus 1x is 5x, so that one works. Denominator is nothing to factor. That's nice and easy. Here I can factor out a 2x, leave me within x minus 1. And here I can see this is a difference of 2 squares, but now I have a coefficient here, which is fine. So that's going to be a 2x minus 1 times a 2x plus 1. Sometimes it might be easier to put the quantities there. Okay, so now you can see the x minus 1's divide out, the 2x plus 1's divide out. That's just going to leave us here with a 2x times x plus 2 all over a 2x minus 1. Okay, with my restricted values of, let's see, x cannot equal 1/2 or just 1. And then if I was to set these equal to 0, that would be plus or minus 1/2. All right, so let's go ahead and work on this one. So again, we have a trinomial raised to higher terms or higher powers. So I figured I remember that correctly. So that'd be a x plus 1 times an x plus 1, x squared plus 1. It would be the factored form. Here, I'm going to want to use grouping. So I'm going to want to factor out an x squared. That's going to leave me with an x plus 1 over an x plus 1. So if you factor out the x plus 1's, I'm kind of doing factoring upwards instead of downwards, which is kind of weird. But hopefully you're familiar with what I'm doing, so therefore you can see that. All right, so let's just go and rewrite this now. So I have 6x squared over x squared plus 1 times x squared plus 1 times x plus 1 times x squared plus 1 all over 2x cubed. So now you can see that my 6 and 2, those are going to divide, right? Those simplify, 6 and 2. So 6 over 2 divides just to 3. And then I have my x squared over x. Well, that's going to go ahead and simplify just to leave me with an x. I have an x squared plus 2, and my x squared plus 2 divide out. And that's an x plus 1, and then that's an x squared. They're not the same, so they're not going to divide out. So that's going to leave me with a 3 times x plus 1 all over an x squared plus 1 times x. And my restricted values, that's going to be imaginary numbers. This would be plus or minus 1. Oops, let's just write x cannot equal. Plus or minus 1. That, when you set it equals 0, gives you, again, imaginary numbers. And then, obviously, the only value that's going to make this 0 is going to be the number 0. So, therefore, that's going to be my restricted value. Okay? And then we went and talked about division. So division is a little bit different. But again, the same kind of thing. You're going to want to simplify first, or look to simplify. Rewrite it as a product of its reciprocal. So you're going to be multiplying by the reciprocal of the divisor. And then we're just going to, again, simplify using the division property. But again, now that you've written it as multiplication, you can divide across multiplication. So, basically, here you have the problem. Divide it. Rewrite it as multiplication. So you can see how my numerator went to my denominator and my denominator went to my numerator. And then you can go ahead and apply your division property here. And then just go ahead and simplify. All right. Now, as far as the excluded values go, I've seen actually a couple different people teach it a couple different ways. The way that I've learned it and I feel like best understands is, again, excluded value is anything that makes the denominator 0. That means as the problem is written as a division problem, what numbers make the denominator 0? When the problem is written as a multiplication problem, what values make the denominator 0? And then what are my final solution? What values make the denominator 0? And obviously you can see that it's just repetition here for the final example, right? But sometimes when we get to further problems, that will actually change. But for right now, the final quotient is always going to be basically the sum of those first 2 examples, or those first 2 operations. But that's the way that I like to teach it, and at least I had my students go and do it, is just look for those values. All right, so the first thing we're going to do is let's just factor, 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 factor. All right, so in this case here, I have a x minus 2 times an x minus 1 all over x divided by, let's see here, that's going to be 3x. I think that's both going to be minus, right? Minus 1 and then x minus 1. And again, I'm just kind of doing a guess and check in my head. I've already covered a lot of factoring problems in my class, so I kind of expect my students at this point to be fairly comfortable. And if they're not fairly comfortable with factoring at this point in my class, then they are supposed to do all the problems that I have given them for factoring practice, because I give my students a lot of problems to practice their factoring. So that'd be an x minus 2. Okay, cool. So there's the division. And obviously, the better you get at this, I'm doing this for kind of instructional purposes. You could obviously just go ahead and skip that step and just go from factor it and then write it like this as a product of this reciprocal, right? And then let's see, minus 1. So now you can see that the x minus 1s are going to divide out. The x and the x squared divide out. Nothing with the x minus 2s, and this 3x minus 1, nothing divides out there. So therefore, we're just going to be left with here, should write an equal sign, 3x times x minus 2, quantity squared, you can write them multiplied out if you want to, all over 3x minus 1. Okay. Now our excluded values are going to be x cannot equal 0, right there, and right there, positive 2. And then here, when we write it as the product, that's going to be a positive 1/3 and positive 1. And you can see there's nothing changed here in our final solution, right? And yep, there you go. Looks good. So for the next one, now here we have this x cubed plus 1. I know many of my students, I kind of gave this away to them as far as for them to understand, but that's going to be the sum of 2 cubes. And if you don't remember the factored form for the sum of two cubes, I don't really feel it's that important for my students to have. Obviously, for those of them that are going on to further mathematics, I think it's important for them to have. But for the majority of my students that are not going to ever probably use this formula ever again, I just wanted them to be really familiar with it. And, you know, I do have this available, or I want to make that available for them on any kind of test and stuff. So, but the important thing, though, to understand when we're doing the sum or difference of two cubes is like this gives you your real solution, and then this gives you your complex solution, which I thought happened. Maybe that came up. Maybe I did. Oh, I did do this example. Okay. I thought I put that in the denominator. I guess not. Okay. So let's go ahead and factor that. So if I was going to factor that using this formula, it would look like this. X plus 1 times x squared plus 1 times x is just x plus 1. All over the factored form here, I could factor out a 2, right? So that's going to be x squared plus 2x plus 1. Okay, so that's going to be an x plus 1. Instead of writing this as x plus 1 squared, I'm going to write this as x plus 1 times x plus 1. Now, I'm going to skip a step here. I'm not going to write the division. I'm going to write it as the multiplication. So just be very careful when you're doing this. Take the denominator and put it in the numerator. So again, whenever you write that multiplication, when you change it, make sure you flip. And then this, you can see, is x minus 1. Oh, that's supposed to be a net. Oh, I messed up. My bad. Yeah, it's opposite sign. So that's plus, and then that's supposed to be the opposite sign. Ah, gotcha. Okay, so actually I didn't do this problem with my students. Or maybe I did a variation, I'm not sure. So this becomes x squared. Yeah, so that's minus there. X squared minus x plus 1. Okay, so now you can see that this whole quantity is going to be divided out with that whole quantity. Here, the x plus 1s divide out, right? Here, these x plus 1s divide out. Leave me just with the number 2. But it's the number 2 where x cannot equal, I think it was, hold on, I'm sorry. I just had to look at one of these fractions I was looking at, bothering me. Maybe I didn't do it. Sorry, I was just, okay. I don't know where I did one of those problems. So x cannot equal, let's see, x cannot equal plus or minus 1. And then, again, if you were to take this, the understanding we worked through these problems in our last unit, x squared minus x plus 1, if you set that equal to 0, you would get complex numbers. So therefore, we can confirm that those are not going to be any excluded values. So my only excluded values would be plus or minus 1. So again, the sum and difference of two cubes is just a factoring technique that we cover. Here's the difference of two cubes, in case you need to know it as well for your class. Sum and difference of two squares is, obviously a lot more common for students and used a lot more often. But now that we've kind of talked about that for polynomials, we talk about that sum and difference of two cubes that comes up, and just to be aware of it, and know how to apply it. And you can see in this case, it was very important. If you didn't know how to factor that using the sum and difference or the sum of two cubes, you wouldn't have got the right answer. All right. So now onto the last one is the simplifying complex fractions. So the reason why I love the complex fractions is because, one, you can't keep, change, flip this. You can, but it gets a lot more difficult, at least to understand the keep, change, flip kind of methodology. The other one is, when I taught Algebra 2, one thing I went over with the students is, you can always just apply the operation. Like if you get stuck in class, or on a test or on a quiz, like if you're doing this first problem, you're like, I don't know what to do. Well, then just add the numerator, add the denominator, and then you're going to have a fraction over a fraction, and then just multiply by the reciprocal, right? So, I actually showed the work over here. I get common denominators, and when I combine them, I get 7/12 divided by negative 1/12, multiplied by the reciprocal, and I get an answer of negative 7. Now, that didn't take me very long, but you can see there's a lot of fraction operations, right? And so if that's your only option, fine. But the way that I like to think about this in this section is to kind of do something completely different than what we have done for the rest of class. I said, why do all of those fraction operations, okay? If you don't have to. Because my favorite fraction was 6 over 1, which is 6, right? My second favorite fraction is when you have like 6 over 2, because 2 divides into 6. Agreed? So therefore, that's actually doesn't, if you just simplify it, you don't have a fraction. So when you have a denominator that actually evenly divides into your numerator, that happens here too. But when you have another factor that divides into your numerator, you no longer have a fraction. So my goal here is then what am I going to do? What can I multiply everything by that 3 and 4, 4 and 3 all are going to divide into it? So basically what I want to do is find the LCD again. Well, the LCD of 3, 4, and 4 and 3 is going to be 12. So I'm going to multiply everything times 12, all right? Everything. So one thing you can do is you can just put everything in brackets and multiply by 12. Now again, when I multiply 12 times 1/3, 3 divides into 12 4 times. 4 divides into 12 3 times. 4 divides into 12 3 times, and 3 divides into 12 4 times. Therefore, that's leaving me with 7 over -1, which is -7, which is the exact same answer I got over there. All right. Over here, I decided not to do these two problems. I kind of changed them. And again, just following the same operation, multiply everything by 12, multiply everything by 12, multiply everything by 12. And the important thing is, what I want you to look at is every single problem. When I multiplied everything by the LCD, which in this case, everything was 12 every single time, notice how I only got one simple fraction, right? Look how many fractions are here. 1, 2, 3, 4, big one, 5. But when I multiply by the LCD, I only have one fraction, right? I just have one numerator and one denominator. That is the power of the multiplying by the LCD when you have a complex fraction. It means a fraction within fractions. Okay, so really all we're going to need to do is determine the least common denominator. We're going to multiply every single fraction by that least common denominator, and then we're just going to simplify. And in this case, though, I left off the complex. In this example, I'm going to leave off the complex or excluded values. Did I? Yeah, I did. Okay, so in this case, for my examples, I showed a little bit. I actually showed the distributing, okay? Because not always is something going to divide out here. Like here, the denominator is 1, right? And so my two denominators here is x plus 2, x minus 2. So therefore, my LCD is going to be the product of those two. When I multiply every single term here, now again, remember, x plus 2, x minus 2 is really also x squared minus 4. That's why when I multiply this times 2, I get 2 times x squared minus 4. Plus, here you can see the x plus 2 divide out, leaving me with a 1 times x minus 2, which is just x minus 2. The denominator here, I get 2 times that quantity, plus here the x minus 1's, x minus 2's divide out, leave me just with an x plus 2. And now it just comes into a simplifying and combining. And I didn't actually look to see if those actually get factored out, which, let's just see. I don't think that's 2x, 5 and 2. Oh, crap, that is factorable. Jeez. So let's see, that goes into 2x. I can't believe I didn't check that. So if I did this as a 2x, let's see, x minus 4. No, not 4, 2. Minus 2, and then this would have to be a -5, so that'd be a 2x plus 5. Let's just make sure that works. That becomes a -4x, that's 5x, so that does work. And then for this one, I'm figuring I'm probably gonna have to do, it's not gonna be 2x plus 5, so I'm assuming it's gonna be x minus 2. So therefore, this would have to be a 2x plus 3. And let's see if that works. It does. So therefore, my actual simplified result here turns out to be 2x plus 5 over 2x plus 3. So got to be very careful when you're doing these problems. Make sure you further simplify them. Again, I got a little bit lazy here and when I was creating all these, and I forgot to check to make sure that the x minus 2's divide out. So just a quick little thing, the excluded values are still going to be the same, but just make sure you kind of simplify them as far as the final step, right? Final step, simplify, and I forgot to do that. Oh, that's step number 3 anyways. All right, next one. Next one has 4 fractions. Fraction of numerator, and then again, look to factor this. You factor out that numerator, 2x plus 1 times x minus 2, and therefore now you have 3 different denominators, x minus 2, the 2x plus 1, and you got these. You identify the LCD, 2x plus 1 times x minus 2. Therefore, that's going to be that product. You multiply everything by there. You can show this distributive property, guys, but obviously if you're multiplying, if this is in the denominator and you're multiplying it by this, those are going to divide out, leaving you just with the number 2. Here, the 2x minus x minus 2's divide out. Here, the 2x plus 1's divide out. So that leaves me with x times 2x minus plus 1, and then x times x minus 2. When I go ahead and combine my like terms, I get 2 over 3x squared minus x. And then again, I did do excluded values over here. Oh, well, I didn't really mean to do excluded values. But you can see here the excluded values are the original denominators, which is 2 and negative 1/2. They also include, but again, now once you get to your simplified answer, you also see that the excluded values are going to now include, I factor out an x to be 0 and a positive 1/3. So the important thing about when you're doing complex fractions for excluded values, which I guess I might as well, I'm going to do over here, is you're always going to look at the original excluded values, the values that make denominator 0 over here, and then once you get to your final answer to exclude the values. So actually, you know what? I guess let's just do excluded values. We're used to it, so it's good to go. All right, so I just got these 4 examples, and I think I gave myself more room. I did. Okay. So I'm actually going to show you also a different way now that I have a little more room to do this. So here, we're just going to find the product of their denominators, right? So you can see the product of the denominators is 2 and x minus 1. So I'm going to multiply everything times 2 times x minus 1. Now, in this case, I got a little more time. So I'm literally going to write out 2 times x minus 1 for everything. Okay, so now you can see the 2's divide out, the x minus 1's divide out, x minus 1's divide out, and the 2's divide out. So I like doing it this way better than really doing it that way as far as like a understanding portion. But you can see that obviously just writing it once, and kind of doing the work in your head makes things go by a little bit faster. So therefore, I'm going to be left with here a 3 times x minus 1. And then here, this is going to be a negative 2. All over, in this case, we're going to be left with a 2 plus a 3 times x minus 1. Now again, my terms are separated by addition and subtraction here, so you can't divide them out, right? But we can distribute them, which I could have done without showing it. I just wanted to kind of show that step. All right, so therefore I'm going to get a 3x minus 5 all over a 3x minus 1. So let's check our excluded values. We know that x cannot equal positive 1 because that makes that fraction 0. 2 does not make the denominator 0, right? That's just a number in the denominator. And then also we have 1/3, right? So if we were to set 3x minus 1 equal to 0, we would get x equals 1/3. So x equals 1/3 also makes the denominator equal to 0. So therefore, that's why it's excluded value. The next one here, we can see the LCD is just going to be a product of x times x plus 3. Now that I've already kind of shown it once, I'm not going to do it again because it's a lot of writing. So I'm just going to multiply everything times x plus 3. When I do that, you can see the x plus 3's divide out. That's just going to leave me with an x times x minus 2. I will show this at least one more step so you guys can see where I get that. Here, the x's divide out, so it's going to leave me with a negative 2 times x plus 3. Over here, the x plus 3's will divide out, leave me with an x times x plus 2. And then here, the x's divide out, leaving me with a positive 2 times x plus 3. Okay, so now it just comes in again to simplifying. So, x squared minus 2x. And you could save your step, right? I'm just doing it to show my work, so therefore people don't get confused or lost. Because, I remember when I was doing math, like that's where a lot of times I would get lost is when a teacher would skip steps. And again, for the sake of time, we have to skip steps, or not show everything every single time. Plus 2x plus 8. But I can definitely see how students, can still get confused. Now, that's not factorable, but I want to make sure that it's not going to be any irrational number. So what I could always do is check the discriminant. If you remember, the discriminant in the quadratic formula is b squared minus 4 times a times c. All right? And, yeah, okay, thank you. So if I did this discriminant, that's going to be under what's in the radical. Now, again, if that number is negative, that means you're going to have complex solutions if you were to use the quadratic formula. And the nice thing here is 4 times, or 2 squared is 4, times a, which is 1, times 8. And what you guys would see is that's going to give you a negative 16. So if you were to do the quadratic formula to solve for this, right, because this cannot be 0 in the denominator, what we would attain would be complex solutions. And again, there we know that we don't have any other restrictions there. We don't need to restrict complex numbers. So therefore, the only restrictions here are going to be negative 3 and 0. All right, moving on to the next two examples. In this one, again, we can see, oh, they have all three different denominators, right? But again, we can go ahead and factor this out. And hopefully, it's not always going to be the case, but it's probably a good wink, wink, that x plus 1 and x plus 2 are going to be the factors there, right? So therefore, you can see that my LCD is just going to be my product of my two denominators, right? Because this one shares both of them. So when I multiply everything times my LCD, let's see here, I'm going to get actually the factored form, x squared plus, let's see, that's going to be a 3x plus 2, if you multiply that out, times 1, plus, let's actually multiply this out. So the x plus 1's divide out, so that's going to leave me with a 2x plus 4, and I apologize if I make a mistake, but because this is usually where mistakes are going to happen, is when you start doing work in your head. The x plus 2's divide out, leave me with an x times x plus 1, so that's going to give me an x squared plus x, minus x plus 1's divide out, x plus 2's divide out, leave me with just a negative 1. All right, I can handle that. So now let's go ahead and combine our like terms here. So we have x squared is my only x squared. 3x and 2x, that's going to be plus a 5x. And then plus 6. Now the interesting thing here is, again, I recognize something that is, again, non-factorable. But I don't want to just say, oh, I'm not going to worry about these restrictions. What I'm going to want to do is go back to my original problem and say that x cannot equal negative 1 and negative 2. But now to actually go and solve these restrictions. So I'm going to set this equal because I don't want any number that's going to make this 0. Now, obviously, if they're imaginary numbers, then I don't need to worry about them. But I tested the discriminant in my head here, and I realized that it's going to work. It's going to give us an irrational number. 4 times a times negative 1. So in this case, we're going to have 1. That's going to be 5. Oops, what happened to my... Did the quadratic form not showing all the work? It's opposite of b, plus or minus, right? 5 over 2. So my restricted values is x cannot equal negative 1, negative 2, and x cannot equal negative 1 plus or minus the square root of 5 all over 2. So again, when you're identifying the excluded values, find the excluded values from the original problem and then from your simplified solution. And this is non-factorable, therefore I knew it wasn't going to divide out with anything else. All right, last example here. I'm going to want to rewrite that as a negative x squared plus x, factor out the negative to give me a x squared, or factor out a negative x, right? So if I factor out a negative x, that's going to leave me with a x minus 1. Okay, so now I have an x minus 1, and a negative. So my LCD in this case is going to be a negative x times x minus 1. So I'm going to multiply everything times all of those three. So here, my x's are going to divide out. But therefore, I'm going to have a negative x minus 1 times x minus 1. So let's see, that's going to be a negative x minus 1 times an x minus 1. Over here, my x minus 1s are going to divide out, so that's going to leave me with a negative x times a negative x. Over, everything divides out over here, leave me just with an x squared. All right, so this is because it's going to produce a perfect square trinomial. which is going to be a x squared minus 2x plus 1. Negative x times negative x is going to be a positive x. Now, all over x squared. Let's go ahead and distribute that. Negative x squared plus 2x minus 1 plus x all over x squared. And let's put it over here again. Let's combine our x. So therefore, we have negative x squared plus 3x minus 1 all over x squared. Nothing's going to like divide out. Don't need to factor it. So therefore, I know that x cannot equal 0 and x cannot equal 1. Those are my only two restrictions from there, from the original problem and then from the simplified version. And again, the x squareds cannot divide out, guys, because that is separated by addition. So really the main thing that I wanted students to work on is you can see how much factoring I just did. I did a ton of factoring, and I probably, hopefully, didn't make a mistake, but it'd be very common, and I wouldn't feel bad if I did, because I just did a lot of factoring. But that's the purpose that I want from this lesson, for you to gain some confidence in your factoring skills, and as well as to be looking ahead as far as looking for things to be factorable and looking for you to be able to identify the division property. But just don't divide things because they're the same. Make sure you can apply the division property correctly and also understand why we have excluded values. So that is how we ended basically the lesson, and then just basically want to see from students, what they understood from lesson, as well as what they kind of had trouble understanding. And then if you guys have any comments from there, I'd love to go and hear them, but I look forward to seeing you guys on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work on graphing rational functions. So these are the notes that I actually went over with my students for this short little chapter that I have for rational functions. We're actually not going to practice graphing, even though I know that's the title, but basically we're going to be able to identify everything that we want to do so that we could graph. Because I kind of stopped graphing rational functions a couple of years back, just with the, with technology and really the use of why we're spending so much time on graphing. It was taking up too much of my class time. So I think there's still some important things that I want my students to understand as far as how to identify the x and the y intercepts of any rational or reciprocal functions, as well as how to identify the asymptotes of a rational functions. I think they still think those are very important points, but the fact of like plugging that stuff in, finding symmetry, plugging in points to get a graph, we have technology that can do that, and it takes too much time, in my opinion, to utilize that for class time. So we're just basically going to work on finding the foundations so that we can graph. So what I did is I kind of started with my students, giving them kind of just some equations, and actually I shouldn't really have that out there, but what I did is I kind of gave them these 3 examples, and I said, all right, let's just kind of think like, what do you guys remember about the x and y intercepts? I gave them like 3 minutes, like see if you can find the intercepts and the asymptotes based on what we've talked about in this class, which has been functions and polynomials. And so basically, most students, hopefully they remember that I have, been talking about for any function, when you want to find the x-intercept, y is equal to 0. And for any function, when you want to find the y-intercept, x is equal to 0. So hopefully be able to identify these. You get x equals 1 and y equals 1/4. And then to find the vertical asymptotes, again, as long as it doesn't get divided out, you set your denominator equal to 0 and you go ahead and solve. Now, I wanted my students to kind of like recognize some things, some little characteristics here that kind of help us out. The first thing is that when we're dealing with a rational function, that means you have one of these where you have a function or a polynomial over another polynomial. And we'll get to the formal definitions in a second. That when you set y is equal to 0 here, or f of x, whatever may be the case, you're always multiplying by the denominator to get the variable off the denominator. So that divides to 1, this goes to 0. So really, you're just setting the numerator equal to 0. So that was something I wanted students to be able to see, because, we don't actually need to show all of this work. And that's kind of a nice thing. Like, as long as we understand what we're doing, we can kind of use some tricks here and say, well, to find the x-intercept, really just set the numerator equal to 0. Now, I had a lot of students that they're trying to memorize it. And I'm like, do I do this? And I'm like, don't memorize that, please. Just memorize x-intercept, y equals 0, y-intercept, x equals 0, because that's true for any function. And you need to know that. However, once you kind of get good at it, you can realize, oh yeah, it's just going to be the numerator equal to 0. For the y-intercept, when these all go to 0, you notice that it's just going to be constant over constant. So, because whenever you plug 0 in for x, you're just going to have whatever the constant is over the constant. So you could plug in 0 and show the work there, right? But you could also just kind of do this little shortcut and say, oh, this is always just going to be the constant over the constant. And then again, the vertical asymptote is again the key thing. As long as nothing divides out, that means it's a whole, then it's just your denominator equal to 0. So based on that kind of information here, I wanted to, let's just go and figure out the rest of the x and the y intercepts, and then we'll talk about any other asymptotes. So, the x-intercept here, if I set this numerator equal to 0, that's going to be x equals plus or minus 1. The y-intercept is going to be constant over constant. And then, let's see here, the vertical asymptote, if you set that equal to 0, it's going to be the same as the last one. So x equals plus or minus 2. Right? So you can kind of see how I actually didn't need to show all of this work. But I wanted my students to see that because we're obviously going to be doing this again in this lesson. Over here, if I want to find my x-intercept, it's going to be the same. X set that numerator equal to 0, so that's going to be plus or minus 1. For the y-intercept, notice again, that's going to be constant over constant, which is positive 1/4. And my vertical asymptote in this case is now going to be x equals 1/4. So now let's go and take a look at the graphs and try to see, well, do these make sense? Do these work? And what about any other asymptotes that may be there? Okay, so now we're looking at the graphs in Desmos. And what you can do is, we already know that this has an x-intercept, and we, talked about an x-intercept at 1, vertical asymptotes at 2 and -2, and a y-intercept at 1/4. And we go and graph it. It looks like, that looks like the case, right? See, we have an x-intercept there. There's my y-intercept. It looks like I have some vertical asymptotes at -2 and +2. And again, asymptotes, remember, is where the graph is approaching, right? So you can see the graph is approaching those vertical lines at 2 and -2. And you could always write them, you could always show a line, but you can definitely see it's approaching these numbers. It also looks though like there's a horizontal value that the graph is approaching. Like as I go to the left, kind of watch what the y value, this y coordinate there, look what it's approaching. It looks like it's getting closer and closer to the number 0, right? And whereas here, my y value gets smaller, 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 and it looks like that's approaching 0. Well, again, if something's approaching 0, it doesn't look like it's going to be crossing, right? It looks like it's just going to continue approaching it. So if something is approaching 0 or approaching a value, that's going to be a asymptote. So it's approaching a y value, so that means it's a horizontal line, so therefore it's going to be a horizontal asymptote. So this equation has a horizontal asymptote at 0. Now, a lot of people will say, well, it crosses at 1 because a lot of times, when we're first learning about asymptotes, it's just easy to remember, we don't cross asymptotes. But that is for vertical asymptotes because vertical asymptotes are discontinuities, right? They are undefined for a function. Horizontal asymptotes are not undefined. They're not discontinuities of a function. So they are just going to be values that the graph is approaching from left to right, or a y value that the graph is approaching, rather than an x value the graph is approaching. So anyways, for the first example, we have a horizontal asymptote at y equals 1. Now again, if we kind of step back here and look at the difference here between the first equation and the second equation, we notice the only thing different is that there's an x squared now in the numerator, right, instead of the denominator. So we did recognize here, though, that the x-intercepts now are 1 and -1, and the vertical asymptotes are still -2 and +2, and the y-intercept's the same. So let's go and take a look at this one, see if it's going to have the same horizontal asymptote. Oh, this one's a little different, right? So we have our new x-intercepts, we have our y-intercept, but now it looks like it's getting to 0, but it's actually, as I keep on going farther to the left, you can see this y value looks like it's approaching the number 1. As we go over to the right, you can see the y value is again approaching 1. And as I keep on zooming out, it doesn't look like it's going to be crossing 1 anytime. So we can maybe kind of conclude that this example has a horizontal asymptote at 1. And then, so then the last one is I always ask students, all right, guys, so what do you think about the last one? Like, this one was at 0, this one's at 1. Now I'm going to take these, squared away from the denominator and just leave it up in the numerator. And, people are like 2, -1, and does not exist. And we'll see. Well, when we go and graph it, we know that there's the x-intercepts at -1 and 1, right? And we had our y-intercepts, so that's true. But then, where did the rest of the graph go? Well, if we zoom out, we can actually see it looks like actually there's a slanted asymptote. Doesn't look like there's a horizontal asymptote. We still have that vertical asymptote at 4, right? But now it looks like there's this angled kind of slant, and that's kind of interesting. So the exact same equation, the only thing I did was change the degrees of the polynomials in the numerator and denominator, and that changed everything with the asymptotes. And that's going to be something that we're going to cover in the class. I wanted students, though, to see it for themselves before we get into the work. So now let's go and get back into the problems, and we'll come back over to this. Okay, so now we can go ahead and update the information here. If you remember, the only thing is when the squared here was in the denominator, we recognize that this had a horizontal asymptote at, what was this? Oh, let's kind of combine these here. So that's there. So this horizontal asymptote was at y is equal to 0. This one had a horizontal asymptote at y equals 1. And this one had no horizontal asymptote. It did have a slant asymptote, but we can maybe come back to that after we learn how to do it, because I don't think we could have really guessed what that slant asymptote was. So if I remember, I will try to come back to this once we go ahead and learn that. So, but before we really understand everything as far as rational functions, I think it's really important for us to kind of take a step back and go back to the reciprocal functions, something that we spent a lot more time in in Algebra 2, as well as in the beginning of my class. So remember, the parent function of the reciprocal function only has one variable unknown. So in case you can see, these were rational functions. They had x's in the numerator and denominator, but this good old reciprocal function just had a variable in the denominator. We had the parent graph here where it looks like this hyperbola, where it has a horizontal asymptote at 0. Horizontal asymptote at y equals 0, vertical asymptote at x equals 0. They do not cross the x and the y intercepts. Here's the equation with all the transformations. One important thing to understand, remember, a is that operation outside of the function, right? So, a lot of times we would just represent the a in the numerator, because if you were to multiply a times that function, right, it's just going to go in the numerator, like whatever it is. So just to understand, though, a is still your outside operation, b is your inside operation. So with the reciprocal function, what is in the denominator is referred to as inside, right? That's going to be your horizontal shift, compression, stretch, and reflection about the y-axis. And just remember, if you have a b, you got to factor it out. A lot of times, if you don't have a b, then you can just treat it as x minus c, and it's easy in that regard. But yeah, that was basically, wanted students to kind of remember that, because we're going to kind of start this with the reciprocal function. So in the first example, what I want to do is just kind of show students, how we find the x and y intercepts with the reciprocal function. Because basically when in this class, we just basically talked about transformations, right? So the nice thing about the reciprocal function is we can really easily identify the vertical and the horizontal asymptotes. Because again, we know that the asymptotes here are at 0 and 0. So if I shift the graph 2 units to the right, if I take this graph and shift it 2 units to the right, the asymptote, the vertical asymptote, is going to move 2 units to the right. That's why I got a vertical asymptote at x equals 2. If I shift this graph up 1, like you can see, this horizontal asymptote now gets shifted up 1. So therefore, that's why the horizontal asymptote is at y is equal to 1. So the reciprocal function is pretty nice, because we can, as long as we understand the transformations, those vertical and horizontal asymptotes are nice. However, you can see that the x and the y intercepts are not as fun, because when we did back these rational equations, we started using these tricks, right? We recognize a lot of these tricks and tips to help us with this. Whereas the reciprocal function, we actually needed, again, go back to plugging y is equal to 0 and plugging x is equal to 0. And then using our inverse operations, make sure when you multiply here by -1 that you distribute, right? So we went back to using those inverse operations to go ahead and solve. And there's really nothing you can do to kind of get away from that. You can't do the trick. You can't just set the numerator equal to 0, right? Because that wouldn't give you -1. You just can't take the constant over the constant, because the answer is -1/2, not -3/2. So again, that's why relying on that basic understanding of the x-intercept y equals 0 and y-intercept x is equal to 0 is going to be very important to work on. So I wanted students to go ahead and practice that, and that's why we went to, so we did a couple more examples, or at least I went through this example, and then we go ahead and practice a couple more. Okay, so into these types of problems, basically we're going to look into just finding the x and y intercepts of the following functions and the vertical and horizontal asymptotes. So I think the basic thing here is to understand the transformations. Now, obviously, there's important things actually to remember real quick, is the only thing that's going to change these asymptotes here is going to be shifting left and right and up and down. When we have a vertical stretch or compression, or when we have reflections, those are not going to impact my asymptotes. The only thing that's going to move those asymptotes is shifting left and right as well as up and down. That's important because I can really disregard this -3, this reflection about the x-axis and this vertical stretch of 3. It is transformations of the function, but they are not going to impact it. So hopefully we recognize that this graph is being shifted, let's see, left 2 and down 1. So therefore, I can just kind of easily now write in the vertical asymptote is at x equals -2. And the horizontal asymptote is at y equals -1. Remember that asymptotes are lines, so therefore we need to make sure we have them as x and y. For the x-intercept, again, we're just going to put y is equal to 0. So 0 equals -3 over x plus 2 minus 1. Is that the same? Oh, it's very similar. Jeez. And then over here, let's go through it. And then for the y-intercept, that's going to be when x is equal to 0. So therefore, that would be y equals -3 over 0 plus 2 minus 1. Okay, so let's go ahead and solve this one. So we're going to add a 1. And then we'll have 1 equals 3 over x plus 2. You can't solve for x when it's in the denominator, so I'm going to multiply by an x plus 2 on both sides. You need to apply distributive property, but thankfully it's just a 1 there. So therefore, that's just going to leave us with an x plus 2 is equal to, that divides out to equal 3. Subtract 2, subtract 2. X is equal to 1. So that is going to be my x-intercept. For the y-intercept here, I have y equals a -3/2 minus 1. And then kind of like what I did in my review, if I need to subtract a fraction minus a whole number, I'm just going to change the whole number to a fraction. This is going to be a -3/2. We can just write minus as a 2 over 2. Therefore, now I have common denominators, so I can just go ahead and subtract my numerator, which is going to give me a -5/2. Let's change that 2 there. Okay. Now for the next one here, we recognize we have a little bit of some changes, with the denominator. So I'm going to rewrite this as, let's see, a -x plus 1. Now I can factor out my b. By factoring out my b, I have a -x minus 1. Okay, so again, the reflections here are not going to be changing my asymptotes. The only thing that I know is now I'm going to be going right 1, and there's no vertical or horizontal shift, right? Or sorry, vertical shift. So therefore, my horizontal asymptote is going to remain at 0. So my vertical asymptote is going to be at x equals 1. My horizontal asymptote is still just going to remain at y equals 0. If I set this equal to 0, and I multiply here, let's remember what we're calling this. That's for the y-intercept, or x-intercept, sorry. So to find the x-intercept, now I can just go ahead and subtract. You can use the simplified form if you like. But in this case, you can see that it's not really going to matter because I get an equation that 0 is equal to -1, which is never true, right? 0 never equals -1. So therefore, there is no x-intercept. So if you are solving for an x-intercept where you're supposed to get some value and you don't get a number, then therefore you can see that it is not going to be true. Or no, there's none that are going to exist. For the y-intercept, I'm just going to plug 0 in for x. And therefore, simple math here, -1 divided by 1 is just going to be a -1. And there you go. Vertical asymptote, x-intercept, y-intercept. Okay, so you can see when we have multiple, both those transformations, obviously how this adds a little bit more of the complexity of the problem. So just a couple more. Again, let's recognize here that this is going to be shift down 1. Okay, so again, there's no horizontal shift. So my vertical asymptote is just going to still be at x equals 0. My horizontal asymptote is going to be at y equals -1, though. And let's see, the x-intercept is going to be, so 0 equals 4 over x minus 1. So 1 equals 4 over x, multiplied by x on both sides. X is equal to 4. Right, I guess I'll just show it. Then for the y-intercept, I get another thing interesting. I have y equals 4 over 0 minus 1. Well, we cannot evaluate 4 divided by 0, right? Or any number divided by 0. So therefore, this has no y-intercept. And again, guys, that makes sense because again, remember the horizontal asymptote, or sorry, the vertical asymptote is at 0. That means the graph is never going to cross the y-axis. Like that is the y-axis. So of course, that's a vertical asymptote. That's a discontinuity. You obviously, if you have a vertical asymptote at 0, you're not going to have a y-intercept. And this last example here, just to identify the transformations, we want to factor out the b. So we have an x plus 2. All right, so now we know we're not shifting 4 units to the left, but we are going to shift 2 units left. All right, so therefore my vertical asymptote is going to be at x equals -2. My horizontal asymptote, though, again, the graph never shifted up or down. So that's going to be y is equal to 0. And again, since we have a horizontal asymptote of y equals 0, we're not going to have any x-intercepts. And you can see how that works. This is just a rational expression, right? We don't have any of the plus or minus. We have basically a fraction. So when I set this equal to 0, I can just basically set the numerator equal to 0 like I did at the beginning. And you can see that that works. For the y-intercept, in this case, again, just plugging 0 in for x. And we get y is equal to 1/4. Okay, so now we kind of went through a little bit of review, a little bit of fraction operations, and some basic things some students to remember. Now it's going to be time into getting into some more formal definitions for rational functions. All right, so now let's go and take a look at some different reciprocal functions. So in the next example, we have determined the x and y-intercepts of the following functions, vertical and horizontal asymptotes. What the difference here is, this is not a reciprocal function. You can see this is a rational function like the one we did before. Now, the nice thing is we can easily find the x and the y-intercepts. So that's what I went with my students. I'm like, if I'm asking you the question, this isn't like what you've seen, just go and find the x and the y-intercepts rather simply. So you find the x-intercept, set the numerator, again, this is a rational function. So you set the numerator equal to 0, go and solve. The y-intercept, you go ahead and find the constant over the constant, and therefore you get y equals -5. So very easy. However, as far as the vertical and the horizontal asymptotes, what I wanted to show students is the relationship between a rational function like this as well as the reciprocal function. So in the end, like when we have a rational function, that's just a division of two polynomials, right? I mean, you have a polynomial in the numerator, polynomial in the denominator. Since these have the same degree, then that means that this polynomial can divide into that polynomial. And you're going to get a remainder, or you could, not get a remainder, then it'd obviously divide evenly into it and you'd have a whole. But if it, divides into it, we need to remember again, it will divide into it. We just need to understand how that is going to be written. So what I did is I said, well, we learned how to do division last chapter. So in polynomials, so I go ahead and do long division here, and I get a remainder of 3. And then I need to remember, we didn't really practice this as much in this class because in Algebra 2 we did this, whereas writing the quotient with the remainder. And basically the way that it works is you're going to have the quotient plus the remainder over the divisor. Okay, so here's your divisor, here's my dividend, here's my quotient, and then here's my remainder. So basically, if I write this as quotient, which was, where'd I get? Oh, I wrote that up wrong. I'm an idiot. That goes into there. I switched those around. So this is actually a -2, and that's a 3. So my horizontal asymptote is not at y equals 3, it's actually at -2. Let's do this. Okay, so when I was doing this problem, preparing this slide, you can see I made that mistake. But again, the important thing is if you divide this into this, another way to write that is, writing it like that, like writing it in terms of this fraction form of the quotient. It's kind of like the same thing. 3 obviously divides into 12, right? Well, what about 5? You could say 5 divides into 12 2 times, with a remainder of 2, right? And we don't really use that fraction form of, 5 and then whatever the fraction would be. And I wrote it for my students and they just got them more confused. But I just want you to understand, like if 5 divides on 12, we know 2 times with the remainder of 2. That's usually how we would just say it. However, the kind of formal way that we could also write it in terms of fractions go, it would be quotient plus remainder over divisor, which is the same thing, even with like numbers. It just kind of looks a little confusing when we look at numbers and nobody wants to do it. But the important thing that I wanted students to see from this case is that now, if we are able to rewrite it, not only are rational functions in this form related to reciprocal functions, but now we can easily identify the vertical asymptote. Now, again, notice we didn't really need to find the vertical asymptote here from the rational function to the reciprocal function, like it remained the same, right? But the key point I wanted to do, the reason why I wanted to do these problems is, one, I wanted students to see the relationship or see remember long division, because we're going to do that in just a second, as well as I wanted students to go ahead and see the relationship of the horizontal asymptote. Because do we see the horizontal asymptote in the original problem? Do we actually need to do division here to figure out what this horizontal asymptote was? And in this case, you can see that no, you actually don't, because where did -2 come from? And some students found it, some students didn't, but -2 comes from this -4 divided by 2. Okay, and we'll come through that once we get into some formal answers or formal definitions. I actually wanted to add transformations. Because the only difficult thing about this rational function is we can basically figure out the x to y intercept, the vertical asymptote, horizontal asymptote now rather simply. But as far as understanding transformations, it's a little bit more difficult. That is why understanding something in the reciprocal form would be beneficial. So what I'm going to do for at least these 4 examples here is practicing and just kind of go through the division to practice. So therefore, we can practice long division as well as identifying the intercepts. But before I do that, I want to find the x-intercept and the y-intercept because those are rather simple. I like that. Right? That's just basically setting the numerator equal to 0. So add 3, set the numerator equal to 0, and therefore that's going to be x equals -3. And the y-intercept is just going to be constant over constant, which would be -3 over -1. So therefore it's going to be a +3. So you can see how easy that is, right? So let's just go ahead and now figure out, let's do the vertical asymptote real quick. Vertical asymptote is going to be x equals 1, and hopefully you guys recognize, since these have the same degree here, my horizontal asymptote is going to be at y equals -1. But let's go ahead and do division and make sure that works. So x minus 1, -x minus 3. Okay, x divides into -x, a -1 times. That becomes a -x. This becomes a +1. Subtract. That's not giving me any. X divides into a -1 times. That becomes a +1. Horizontal asymptote, y equals -1. -3 minus 1 becomes -4. Oh, geez, that's a vertical stretch. Okay, I'm sorry. You just saw me thinking about this. Because again, I was like, oh, it's going to be a remainder, but remember it's a remainder over divisor. So we're going to take our quotient. So it's going to be y equals -1 plus my remainder over my divisor. And the reason why I was thinking in my brain, I'm like, oh no, this has a horizontal asymptote of -4. And it's like, no, silly. That is your remainder, which goes above in the numerator, right, of your fraction. But hopefully you guys can see, based on these transformations, the graph is being shifted 1 unit to the right and 1 unit down, and therefore it makes sense. Because again, remember that -4 is a vertical stretch as well as a reflection. That's not going to impact the asymptotes. All right, let's go ahead and do the next one here real quick. X-intercept, y equals x equals -3. Y-intercept, y is equal to 3/2. So you can see how I'm doing this rather simply now, right? Vertical asymptotes, x equals -2. That's where I got the horizontal asymptote. Horizontal asymptote, y is equal to 1. And again, let's just go ahead and write this in reciprocal form. So x plus 2 divides into x plus 3. X goes into x one time. That's x. 2. Subtract your rows. 1. So therefore, that's my remainder. So therefore, I'd have y is equal to 1 plus or minus 1 over x plus 2. And again, you can see shifting left 2 and up 1. Perfect. These are going pretty quick. I kind of like these. Is it the same? No, similar. All right, so in this one, again, let's have the x-intercept here is going to be x equals -3. Y-intercept is going to be y is equal to -3. Vertical asymptote. This one sometimes, again, students will make mistakes, so I'm just going to set it equal to 0. -x minus 1 equals 0. Add 1, divide by 1. X equals -1. Horizontal asymptote, y is equal to -1, because really that's a 1 over a -1, right? And again, remember, we're just finding those reciprocals there. And then when I do division here, I'm going to have a -x minus 1 divides into x plus 3. So that goes into their -1 times. That's a -x. That becomes a +1. Subtract your rows. That becomes a 2. So therefore, you'd have y equals your quotient plus your remainder over your divisor. And you can see that's exactly where we get our examples there. And then to the last example, again, find the x-intercept. We have 4x minus 3 is equal to 0. So x is equal to 3/4. The y-intercept is going to be, again, my constant over my constant, which is going to be a -3/1. So it's just going to be a -3. My vertical asymptote is going to be my denominator set equal to 0. So x equals -1/2. And then the horizontal asymptote is going to be these, again, these coefficients here, which is going to be y is equal to 2. Let's just go ahead and do the division again, just real quick, just to make sure that those asymptotes make sense based on the transformations of the reciprocal function. That goes into there 2x times, so that's 2x times a, oh, that goes in there 2 times, geez, not 2x times. And that's +2. -3 minus 2 is going to be -5. That's your remainder. So y equals my quotient plus my remainder over my divisor. And again, you can see the horizontal asymptote shifting up 2. My vertical asymptote is going to remain the same. Okay, so these are, again, rational functions. So let's actually kind of formalize this here a little bit and actually start talking about the definitions. Basically, again, guys, the rational function is really just when we're going to have a polynomial in the numerator. A lot of times I just wrote this as n of x, and the polynomial in the denominator d of x. Remember that the d of x cannot equal 0 because obviously it's a fraction, but they're both polynomials. And the both polynomials is very important for a rational function because if they're polynomials, that means they're going to have a leading coefficient and a degree. And to understand, remember, or to find the leading coefficient and degree, remember we want to make sure we have the polynomials in standard form. So basically, here's that kind of process that we kind of talked about as far as finding the x and the y-intercepts. When it's in rational form, not a reciprocal, but when it's a rational expression, you always set y equal to 0. Like always y equals 0, or for the y-intercept, x equals 0. But these are some kind of, processes. These are like some tricks to make things go by a little bit easier. For you. So that's what we'll kind of cover rather quickly. The important thing also when we're getting into this is understanding the differences between asymptotes and holes. This is something we already covered in my class in chapter 1. So it's really a review in this section. But remember that asymptotes and holes are both discontinuities, but vertical asymptotes are what we call non-removable because they don't get divided out, whereas holes are removable because they could get divided out. So you can see, when you have a rational expression, I factor it. And since my quantities are separated by multiplication, I can divide them out. But again, you just can't divide like the x's and the 3's, right? You have to divide the quantities here. And you can see that the quantity x plus 1 and x plus 1 are the same. So therefore, I can divide those out. And you can see I kind of wrote down my answer for my discontinuities here, as far as where the vertical asymptotes in the holes, because where there's a vertical asymptote or hole occurs from where the values make the denominator equal to 0. So now kind of getting back into our horizontal asymptotes, like how do we understand the horizontal asymptotes? So kind of going back to this, I'm using a lot of letters here, and I think it's kind of too many letters in reality. So that's why I was kind of cautious with my students when they're writing down the notes. But basically, you're looking at a rational function. So if you're dealing with polynomials, you're going to have degrees. Well, there's only really 3 options on how you can compare those degrees. Either the degree in the numerator is larger than the degree in the denominator, either the degrees are the same, or you have a degree in the denominator is larger than the degree in the numerator, right? Because these are basically a 1 here. So it doesn't really matter what's the rest of the polynomial. All that really matters is, what is the leading coefficient and the degree, like the highest power, right? So, and that's basically what all of this is saying. Here's just kind of some examples. But basically, when the degree in the numerator is larger than the degree in the denominator, there's no horizontal asymptote. When the degree in the numerator is equal to the degree in the denominator, the horizontal asymptote is the ratio of the leading coefficients. You can see A over B, where A is the leading coefficient of the numerator, B is the leading coefficient of the denominator. And then when the degree in the denominator is larger than the degree in the numerator, the horizontal asymptote is going to be y equals 0. So those are kind of just your 3. It doesn't matter what the numbers are. You only have 3 options. You just need to basically kind of know how those work out. So basically, the kind of questions we're going to solve from here is really just determining the horizontal and vertical asymptotes as well as the x and y intercepts. And in this case, I'm basically just saying all these examples are going to be when n is greater than m. So therefore, the nice thing about this is the horizontal asymptote is really easy to find. Like whenever the degree in the denominator is larger than the degree in the numerator, horizontal asymptote y equals 0. The x-intercept, set the numerator equal to 0 and solve. Set the y-intercept. Y-intercept's interesting because there really technically is no constant, right? So you could say 0 over 0. But again, you cannot divide by 0, so therefore it is not 0, but it is none. And the vertical or it's not 0 or it's not 1, right? Some people will write 1 or they'll write 0. But again, you cannot divide by 0, so therefore that's why there is no y-intercept. And the vertical asymptote, again, is going to be the values that make the denominator equal to 0. However, actually, I can't believe I didn't check this. If you were to factor this out, like if you write this in factored form, 2x times x plus 2. The x is actually divide out, so that is actually a whole. So the only vertical asymptote is at x equals -2, right? Because these x's divide out. The 2's, even though they divide out, those are scalars. Those do not, 2 does not make the denominator equal to 0. -2 makes the denominator equal to 0 because that's in the factored form. So just understand, though, that x equals 0 is going to be a whole because even though 0 makes the denominator 0, it gets divided out. So that's why it's a whole. And actually, I didn't catch that when I was going to my answers. So let's go ahead and work on this again. That's what I was thinking of. I knew I was going to come up to that problem. All right, so let's go ahead and find the x and y intercepts here real quick. So the x-intercept is the numerator equal to 0. 2x minus 2 equals 0. Add the 2, divide by 1, x equals 1. Let's see, the y-intercept is going to be constant over constant. So that's going to be y equals -2 over -5, which is a positive 2/5. The horizontal asymptote is going to be rather simple. That is, larger in the denominator, so that's y equals 0. And the vertical asymptote is basically going to set this equal to 0 and go ahead and solve this. And let's see, that factored form is going to be what two numbers multiply to give you -5, add to give you -4. So therefore, x is equal to 5, x equals -1. I can factor out the numerator to make sure nothing divides out. And actually, it's close, but it's not the same. And again, make sure my factored form is correct, which it is. So therefore, there are no holes because this is, if you were to have this in factored form, nothing would divide out. Because again, for those quantities divide out, they have to be exactly the same. And even though they're really close, they're not going to divide out. So for the next one, x-intercept is, again, x equals 0, kind of easy. Y-intercept, again, you can treat this as a 0, is going to be 0 over -8, which would be y equals 0. Horizontal asymptote is very easy. Now the vertical asymptote is something that we don't really cover as much, but we recognize this as the difference of two cubes. And this is something I did cover in the first lesson just to kind of remind students of it. So the factored form of difference of two cubes. So let's kind of go back through this. I did provide this to my students. A cubed minus B cubed is going to be A minus B times A squared plus AB plus B squared. Okay, now the important thing though that I really wanted to cover with this, if you were to factor this out, so again, you got to rewrite this as a cube term. So 8 is 2 cubed. So you could write this as 8 cubed minus 2 cubed. So therefore, you can see that's where I got that 2. And then this would be x squared plus 2x plus 4 equals 0. Okay, but the important thing that I really wanted to bring up here is there's actually only going to be one vertical asymptote, x equals 2. Because you could also, like in the same respect, you could, add 8. If you remember in our polynomial unit, x cubed equals 8, x was equal to 2. So one times we did that in the polynomial unit, but what we did is I told students, when we're trying to find the zeros of this polynomial, we have to have 3 zeros by the fundamental theorem of algebra. Well, in this case, we're solving, we're finding the solutions. But the important thing is we understand there's only one real solution here. That's going to be at x equals 2. The other solutions that come from here, when you do quadratic formula, those are complex solutions. So therefore, complex solutions are not going to make asymptotes, right? We're only looking for the real solutions. So therefore, this is your real solution. These are your complex solutions. So, you could kind of cheat your way by just using inverse operations to solve from this. But I just wanted to also make that representation as far as what we learned last chapter, not to forget about that, but to understand why we're only taking into consideration the answer of 2 instead of the rest of this. All right, that's fun. Let's keep on doing some more. So next one, I probably want to rearrange this first. X squared plus 1, and then I'll factor out the negative. So whenever I'm doing anything in these problems, I always like to look at the problem like this. Okay, I like to have it a factor form. I want to have any common factors factored out, right? And therefore, I also want my leading coefficient to be positive. All right, so to find the x-intercept, I'm going to set the numerator equal to 0. Well, 3 does not equal 0, so therefore there's no x-intercept. For the y-intercept, now in this case, we don't need to go back through this form, and actually you don't want to go back through this form because you can see that this is being multiplied by -1. So we can just go back to my original problem here and just say that is going to be y equals 3 over 1, which is just equal to 3. Horizontal asymptote is very easy. That's going to be y equals 0. And my vertical asymptote is really, you don't really need to set this in there. I just wanted to kind of see what was going on. But in this case, I can actually just solve using inverse operations here. Set my vertical asymptote equal to 0. There's nothing that's going to factor out with the numerator. So I can just write that as x squared is equal to 1. And just make sure if you're going to introduce the square root of both sides, x equals plus or minus 1. All right, last example here. I can't factor this. Looks like difference of 2 squares. You could, but you could factor this across irrational numbers if that's something you're comfortable with. Since the linear factorization, if you're not, don't worry about it. I'm not going to do it that way for the other problem. But let's go ahead and factor out a x here. That would be leaving with an x squared plus 1. Okay, so anyways, to find the x-intercept, I wouldn't probably factor it, but I want students to make sure that they can do that from our polynomial unit. But I think probably the easiest thing to do would be adding the 5 to the other side and then taking the square root. But I want you guys to understand why I'm using plus or minus the square root of 5, right? Because that is that factored form. For the y-intercept, here I have nothing in my denominator, right? So that's basically 5 over 0. So no y-intercept, right? Because you could put like a 0 down there. Horizontal asymptote, you just got to love it. Y is equal to 0. And my vertical asymptote is going to be my denominator equal to 0. And the nice thing is looking at this in factored form. So I can now apply the 0 product property, right? So therefore x equals 0 and x squared plus 1 is equal to 0. Well, like in the last example that we worked at, x squared plus 1 is going to give us complex solutions. So my only vertical asymptote is going to be at x is equal to 0. right? So x equals 0 is going to be, I don't know why I cancel those out. So x equals 0 is going to be my only vertical asymptote. This is not going to produce, those are going to be complex. Okay, so they're not going to be any real asymptotes. All right, now let's go and work into some examples where the degrees are exactly the same. So really everything is exactly the same. The only difference now is that our horizontal asymptote is not going to be 0 anymore. It's going to be the ratio of my coefficients. And if you don't have a coefficient there, remember we can use 1. So in my case, I set my numerator to 0, and what do you know? I got something that was non-factorable. So therefore, I had to use the quadratic formula to get these crazy x-intercepts, but it's possible. The y-intercept was rather easy, -1/2. Vertical asymptote, thankfully, I had something that was factorable. So I factored it when a was not equal to 1. And then my horizontal asymptote was y is equal to leading coefficient over leading coefficient. So you can see in my work kind of what I did. And then obviously we worked through some more problems. I'm doing that. But let's kind of go through the same steps that we did before. The x-intercept is going to be 2x squared is equal to 0. So when you solve that, x equals 0. Y-intercept, again, is going to be y equals 0 over -3, which is just going to equal to 0. Horizontal asymptote is going to be y is equal to leading coefficient over leading coefficient. So that's going to be 2 over 1, which is 2. And vertical asymptote is going to be x squared plus 2x minus 3 equals 0. Let's hope that's factorable, which it is. What two numbers multiply give you -3, add to give you a +2. So therefore, x equals -3 and x equals 1. All right, so for the next example, let's kind of go through. X-intercept again is setting my numerator equal to 0. I'm going to factor out the 3 because I recognize that. X squared minus x minus 1. That's not going to be factorable. But, yeah, dang it. Are you serious? All right. So that's not going to be factorable, so that's not any fun, but let's go ahead and figure it out. Again, I'm going to want to use the quadratic formula for here. I don't want to use the 3. That's going to make the quadratic formula even more difficult. So it's going to be 1 plus or minus the -1 squared minus 4 times a times c all over 2 times a. Again, I'm not using this 3 because the 3 technically, the first step I would do would be divide by 3 on both sides, right? So my x-intercepts, let's see, that's going to be 1. That's going to be square root of 5. So 1 plus or minus the square root of 5 over 2. I should have done one that was non-factorable. Jeez. Or that would have given me an x-intercept. Hopefully I did one of those. I think I do. All right, the y-intercept is, again, I don't have a constant here, so therefore that is going to be none. Horizontal asymptote is rather simple, leading coefficient over leading coefficient, since they both are squared, so y equals 3/2. And then my vertical asymptote is, I'm going to set this in factored form, so factor out a 2x. That's going to leave me with an x minus 1 equals 0. So therefore, x equals 0 and x equals 1. Again, x is not equal to, that 2 gets divided out, right? So that's a scalar. Make sure you're not making that mistake. All right, and then let's do a couple, last one, or last two. So remember, that's a 1 here in front. There's a 1. Okay, I knew I did one where it wasn't factorable, but it was imaginary. All right, so to find the x-intercept here, I have x squared minus 1 equals 0. So therefore, add the 1, take the square root. So x equals plus or minus 1. The y-intercept is going to be y equals -1 over -1 equals 0 equals 1. Horizontal asymptote would be y equals 1/2. And the vertical asymptote, hopefully it is going to be factorable, is going to be 2x squared plus x minus 1 equals 0. So therefore we have 2x times x equals 0. So let's see, we need to get to -1. So that's going to be +1 and -1. So therefore I can go and solve. X is equal to 1/2 and x equals -1. Yeah, there we go. I had one more thing I want to talk about before the asymptotes, or before I'm done with this, but we'll we'll get to that. Hopefully I'll remember that at the end. All right, so and then for this example, I'm going to have x-intercept is going to be this x squared plus x plus 4 equals 0. Now, hopefully you understand that this is going to be complex, but if not, what we can do is what we call the discriminant, the b squared minus 4 times a times c. If that number is negative, then you're going to have complex solutions, meaning no real solutions, therefore no real x-intercepts. So automatically, I can kind of see that this is going to produce no real solutions. 4 times 1 times 4, right? This is basically 1 minus 16, which is a negative 15. So therefore, there are no x-intercepts. So that's just one thing to kind of look at ahead of time. I didn't need to do the whole quadratic formula to be able to determine that. To determine the y-intercept, though, we need to understand what is this? Like, we got to make sure this is x squared, right? So if we write this in factored form, this would be x squared minus 2x plus 1. So really, we're going to have y equals 4 over 1, which is just equal to 4. As far as my horizontal asymptotes, they both have a coefficient of 1. So that's going to be y equals 1 over 1, which is just 1. And my vertical asymptote, I don't need to use the factored form. I could use this, this form here. So that's x minus 1 equals 0, so therefore just x is equal to 1. It has a multiplicity, but we're not doing multiplicity, right? We're finding the asymptote. But that's basically what we can do now when the degrees are the same. So we cover when the degree in the denominator is bigger than the degree in the numerator. We cover when the degrees are the same. The only one we have not covered is when the degree in the denominator is smaller than the degree in the numerator. And when that happens, we are going to have an oblique asymptote, also known as a slant asymptote. Now, it's important that this does not always happen when there is no horizontal asymptote. There could be the case of a hole. And this is actually a mistake I made with my class. I forgot to actually kind of highlight that this year. And we worked on a problem. I had to actually add this problem in because students were working through the problem. So here's some examples we did. Same kind of thing, doing quadratic formula. Notice there's no x-intercept. Notice how I used the discriminant there. Looks like we found the y-intercept, the vertical asymptotes, horizontal asymptotes, right? But if you look at this next example, a lot of people are like, oh, okay, I'm just going to do my long division, like degree in the denominator, small in the degree in the numerator. But what we recognize here is the x plus 5s actually divide into it evenly. So there is no horizontal asymptote. When you actually graph this, if you plug this into a graphing calculator on Desmos, you just get a line x equals -1 with a hole when x is equal to -5. So it's a line with a hole, and that's it. There's no asymptote there. So it's important that you always got to look for holes. That's why our first step for all of these problems is to simplify, factor and simplify. Because again, especially now when we're graphing, we need to understand when we're dealing with asymptotes or holes. And remember, holes are removable. So let's go ahead and work through some problems here. All right, so we're going to do the same kind of thing. The nice thing is we don't need to list the horizontal asymptote because we know that the degree in the denominator is smaller than the degree in the numerator, so there's not going to be a horizontal asymptote. Oh, and I didn't really say it, but as you can see, to find the slant asymptote, did I not work it through at all? I'm an idiot. It's not y equals -2. What am I doing? To find the slant asymptote, all we simply need to do is divide. So you can see from the definition, to define the slant asymptote is basically the quotient. So actually, let me write this in the notes. So the slant asymptote is just y equals quotient. So we're not going to deal with the remainder. Once we get kind of to the end of the year, we kind of talk a little bit more about that as far as how that works and why we can just drop and get rid of the remainder. So obviously, since the degree in the denominator is smaller than the degree in the numerator, then that divides into that, right? Hopefully I didn't. Yeah, let's connect this across. All right, so let's go ahead and divide for this problem. This one obviously doesn't divide in, it divides into it evenly, but that doesn't produce a asymptote, that just produces a line. But let's go and take a look at this one for the slant asymptote. Good thing here. So -4 x squared minus 6x minus 4. I guess I'm changing this problem. All right, so 2x divides into a negative 4x. I think that's what I may want to do. I don't know. 2x divides into negative 4x, negative 2 x times. Negative 2x times negative 2 is a negative 4x. Negative 2 times negative 2 is going to be a positive 4x. Subtract. I get a negative 10x. 2 divides into negative 10x, negative 5 times. Negative 5 times 2x is a negative 10x. Negative 5 times negative 2 is going to be a positive 10. You can bring down the negative 4. And now when we subtract here, 4 minus 10 is going to be negative 14. And that is going to be a remainder because 2x does not divide into a negative 14. However, my slant asymptote is just going to be the quotient, negative 2x minus 5. Okay, so we don't need to include the remainder. And again, that's something that I'll talk about, at the end of the year, at least with my students, as far as why that is. And basically, if you just kind of look at the graph, it's basically kind of goes into with limits. And as far as that remainder, what we kind of talked about actually last class period goes to 0 as you keep on expanding that out. All right, so now let's just go and work through some more problems. So same exact thing. Let's find the x-intercept, the y-intercept, and the asymptotes. So x-intercept is, again, x squared minus 3x minus 4 equals 0. So that's x minus 4 times x plus 1. X equals 4, x equals negative 1. My y-intercept is going to be, see here I do it over again anyway. So y equals negative 4 over 2, which equals negative 2. My vertical asymptote is pretty easy in this case. X plus 2 is equal to 0. Now, does this factor out? It doesn't, but it is important to kind of write this to make sure, like in factored form, so you can see how it doesn't divide out, right? So therefore, x equals negative 2. And then I know there's no horizontal asymptote, so to turn my slant asymptote, I am just going to divide x squared minus 3x minus 4. And I'm kind of gotten pretty good at this. X divides into x squared x times x is x squared. X times 2 is a positive 2x. And I know that if I'm going to be getting a line here, then once I get my constant, I'm kind of done. Like x is not going to divide into a number, right? So subtract your rows, and I get x. X divides into x one time. So therefore, I'm done. I'm not going to be able to do any other division there. In this case, it's always good just to, again, as I mentioned, divide them out so you can see how that works. Nothing divides out, so therefore my x-intercept, you could use the factored form, or you can just use the, x equals plus or minus 2. For the y-intercept, you can see here that's going to be 4 over 1. So y equals negative 4 over negative 1, which equals 4. Vertical asymptote, let's just I think we're kind of getting ourselves a little easy here. Slant asymptote, though, let's do the division. So x minus 1 divides into x squared minus 4. So how many times is x? Actually, I just have to. X minus 1 equals 0. X divides into x squared, x times. X times x is x squared. X times negative 1 is a negative 4x. Now, in this case, it's kind of important because we don't have anything to subtract, right? So what I'm going to do is I'm actually going to include some place values. Plus 0x minus 4, just to make me feel a little better, okay? Now, you don't need to do this, but I want you to see when you're subtracting 0 minus a negative x is going to give you a positive x, right? So that's very important because a lot of people see, oh, you're subtracting x, it's giving me a negative x. Well, no. You're subtracting a negative x, so therefore it turns into a positive. X divides into x a positive one time. Any other division, guys, you're going to have a remainder. So therefore, that's why that's y equals x plus 1. All right, last two problems to go. Dang, another factoring problem. Oh, man, getting that factoring practice, aren't we? All right, so the x-intercept here, we're going to have 2x squared plus 5x minus 3. Equals 0. Let's see here. I think I got it. 2x, x. Let's see. I want that to be a positive 3 and this to be a negative 1. And I think that works. Negative 2x minus 1, x plus 3. That becomes 6. Yep, very good. So therefore, x equals 1/2 and x equals negative 3. For the y-intercept, again, constant is 0. So therefore, there is no y-intercept. For my vertical asymptote, that is just setting the denominator equal to 0. It's like as basic as you can get. X is equal to 0. And then for the slant asymptote, we're just going to divide x into 2x squared plus 5x minus 3. So x divides into 2x squared, 2x times, right? That gives you a 2x squared. Subtract. And then you're just left with 5x. X divides into 5x plus 5 times. So therefore, y is equal to 2x plus 5. All right, last but not least, x-intercept, numerator equal to 0, x equals 0. Y-intercept, constant over constant. So this is, again, going to be 0 over negative 6. That's y equals 0. Vertical asymptote, let's go ahead and set that equal to 0. Add the 6, divide by 3. So x squared equals positive 3. Square root, x equals plus or minus the square root of 3. So you're going to have some irrational vertical asymptotes, which is perfectly fine. And then to do slant asymptote, we're going to do some division. So again, we have 2x squared minus 6 divides x cubed. So 2x squared divides into x cubed. This one's kind of a weird one. So 2 doesn't evenly divide into this, right? So again, the best way I like to think about this is x, how many times does 2x squared divide into x cubed? Well, that's just going to go into there 1/2 x times, right? The 1, like you can just say there's a 1 in front of there. That's going to remain the same, right? And then that can be reduced down to x cubed divided by x squared is just x. So that answer is 1/2 x. Then we multiply 1/2 x times 2x squared is going to be an x cubed. And then 1/2 x times negative 3 is a negative 3x. I'm sorry, that's a positive x. I don't know what I was doing. And that's a negative. All right, so now we go ahead and subtract our rows. And therefore, that gives us 0. And then this is going to be minus the 3x, which again, kind of going back to that 0 point, is going to give us a positive 3x. And then you can see that 2x squared does not divide into a 3x. So that's it. So y is equal to 1/2 x. And that's it. So we're just going to have that line, y equals 1/2 x. So there you go, ladies and gentlemen. That was basically our chapter on graphing rational expressions. The one thing I wanted to mention to you is, to me, it's very important that students know how to find the x and y intercepts, the vertical asymptotes, the slant asymptotes, and horizontal asymptotes, and the holes. Another thing, if you were to graph them, basically once you identify this point, I think it's important to also identify symmetry. That would mean identifying if the function is even or odd by evaluating for negative x. That's something we've covered in the class, but it's just an added point to the problem to really determine that. And really why that is helpful when graphing without a graphing calculator is therefore if you choose a point, if you know something's even, you can find another point on the graph. So it allows you to quickly find points on the graph using symmetry. Because otherwise, once you've identified these points, you're basically now going to want to use a table of values to plot points to get an understanding of what the graph is going to look like. But for my class, we don't have to graph. And if we do have to graph later in the year, it'll be calculator based. But overall, hope you understood a little bit of this lesson. Hope, what I ask my kids is always to reply, some things they understood, some things they're having trouble with, and feel free to add anything down in the comments, and I'll be more than happy to help you out down below, and as well as see you on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I'm going to show you how to solve rational equations. Now, this is actually the last and final section in our chapter on rational functions for my pre-calculus class. So what I'm going to do is I'm just going to kind of work through my notes and kind of work through some of the answers and show you some of the work that we did in class. So therefore, I can kind of round out all of the examples, and I hope to also help you along with understanding how we want to approach solving rational equations, as well as the process to do that. So what I did though was, at least in my classes, I start off with my students giving them like 3 minutes to see how many of these equations they could go ahead and solve. Obviously, I didn't give them the work, but what I did was I provided, basically gave them and said, go and work. Now, a lot of students, they do the first problems rather easy, but then once they started to see more and more fractions, they started to slow down. They started to do fraction operations. So the work that I showed is basically by me multiplying by the number 2. And if you notice, at least in the first 6 examples here, 2 is what we call the least common denominator. If you multiply every single term by 2, you would get rid of the denominators, right? So this is something that we talked about in previous sections, that, if we want to get rid of our fractions, we can multiply by this common denominator, or we talked about it when we were simplifying complex fractions. For instance, like look at f. If I multiplied everything by 2, not only am I going to produce an equivalent equation, but now I'm just going to have the equation x plus 1 equals 3, and that's easy to solve, right? The LCD does change here as we get to G, H, and I. You can see that here it's the product of my denominators, 2 times 3, which is the LCD is 6. So therefore I multiplied everything by 6 here. Here again, the LCD is 6. You're not going to want to multiply 2 times 3, then times 6, because you can see that 2, 3, and 6 all divide into 6 in this example. And then again, in this example, you can see that the LCD was 12. So that's what I multiplied by, and then just simplified, and it made doing the work a lot easier. And then I kind of worked my way up to, for my students, as far as getting, so, well, what about if we have some variables in the denominator? So kind of did the same thing, gave them like 3 minutes and said, all right, let's go ahead and see how far you guys can get. And from here, we kind of worked on some, certain understanding that we needed to know when we're solving for equations when our variable x is in the denominator. And one is we can't have our variable in the denominator, right? We have to get the variable off the denominator. Now, you could just multiply by the LCD in this case, for this example. You can multiply by the LCD, but the other way, I'm not sure why I actually did that example this way. But if you subtracted the 1 to the other side, you get 2 over x or 2 over x equals 2. Well, again, to solve for x, you're going to want to multiply by x on both sides, right? So therefore, you'd have 2 equals 2x, divide by 2, x is equal to 1. So that is another way to approach that first problem. But basically what I was showing my students is, use inverse operations. Like for these first 2 examples, we can just go ahead and apply inverse operations to go ahead and solve. It's, the main thing is after we subtract the 1, once we've isolated now our fraction, I just multiply by my denominator on both sides, make sure you keep the parentheses so you do distributive property, and then you can go ahead and solve. But that worked when we had one fraction. And you can see that once we start having more than one fraction, inverse operations don't really become as ideal anymore. Like what inverse operations are you going to want to apply here? Now in this case, I actually multiplied by the LCD on both sides. And I'm not sure why, I guess I just didn't show that. So each one of these I can multiply. So here I basically multiply by my LCD of the product of these two, x times x plus 2. Whereas here my LCD was equal to 2x. Here my LCD was equal to 2x. I did these very, very quickly as well. Here my LCD is equal to 2 times x plus 2. Okay, so that's what basically I was multiplying everything by when I was go ahead and solving these. So that's what I multiplied. That's what I multiplied each of those equations by to get to my second equation. Now, obviously, again, this was for some practice versions. So I did slow down and teach my students K, O, and Q so they could kind of see how things were working out. We didn't talk about excluded values in this case, or checking the solutions, because obviously that's going to be a part of our curriculum. But the main thing that I really wanted students to come away from this is if you can identify the LCD, notice how the second step in every single one of these problems is all an equation, right? There's no more fractions anymore. So by multiplying by this LCD, I eliminate my fraction. And that's very important. And then we kind of ended here with getting to R. On the R. And when R, what we notice is this is the only example where I actually got 2 solutions. And therefore, when I plug in those 2 solutions, because remember, like if you find a solution and it's going to make sure that equation is true. So when I plug these values back in to like make sure it satisfies them, I recognize something that's interesting. -2 actually makes this fraction denominator 0. Well, that's undefined. That doesn't work, right? So therefore, that is what we call an extraneous solution, which we move down. So then that prompts me to say, well, whoa, let's make sure we go back and check to make sure any of our other solutions weren't originally excluded values. And it's a really quick check, and you can see that none of the other values or problems that we did had an extraneous solution. So therefore, we just need to really understand what it is this extraneous solution is. So extraneous solutions are basically a solution to a simplified version of an equation that does not satisfy the original equation. So let's look back at what we have. So I had 2 over x plus 1 over x plus 2 equals 3. That is my original equation, right? Now, obviously, when I multiply by the LCD, I get this nice, lovely quadratic that looks like this, 3x squared plus 3x minus 4. Now, forgetting about the original problem, if I was just going to look at simplifying this this equation, like that's from, Algebra 1, Algebra 2, I can just go ahead and factor that, to go ahead and solve quadratic formula, factoring, whatever may be the case. But I am going to have 2 solutions here. And so even though these are 2 solutions for this equation, when you plug these values back into the original equation, you recognize that they make, or at least -2 makes this fraction 0. So like you can see that 2 over x plus 1, oops, let's do this. 2 over -2 plus 1 over -2 plus 2 does not equal 3, right? Because that is a no-no. I'll just write undefined. So that's undefined. So of course it's not going to equal 2. So if it satisfies the simplified equation, but it does not satisfy the original equation, that's why x equals -2 is extraneous. And when I mean extraneous, it just means it's not a solution at all. Okay, so a lot of times we'll find it as a solution, but if your only answer is extraneous, then you have no solution for your equation. And we will have some problems like that as well. So then I kind of went through 2 examples for my students. Basically just kind of reminded them, so the main idea here is basically identifying the LCD, multiplying our equation by our LCD to eliminate my denominators. Like notice how each one of these, right, now does not have a denominator, right? And then I just keep on simplifying to solve. Make sure you notice the difference here between my linear equation, right? When linear equations, that means x is raised to the, to the first power, right? So you can just combine like terms, get the variable to the same side using inverse operations and solve. Obviously, make sure you check -13, make sure that it's going to work. But that's kind of it. The difference here is in the second example, when I multiply by my LCD, my simplified equation is not linear. It's not like this. It is a quadratic. So that is a different process that we need to do to solve quadratics compared to linear equations. And a lot of students, since we, once they get used to doing linear equations, they kind of totally forget what we did for quadratics. Quadratics has a x that's squared and a linear x, right? Or not all quadratics, but at least, for it to be a quadratic, you have to at least have an x squared. If there was only one x squared, you could use inverse operations. You'd have to use the plus or minus form, but you could use inverse operations. But whenever we have an x squared and the x, a linear x, we have to either use factoring, completing the square, or quadratic formula to go ahead and solve. And that's where a lot of students made their mistake in my class on their quiz, is they kind of completely forgot how to solve quadratics. But in this case, this one was factorable, but I recognize that I get my 2 solutions, x equals 6 and x equals -1. However, going back to the original equation, you can see that 6 makes my original equation undefined, so therefore it is extraneous and not an actual solution to the equation. All right, so let's go and take a look at kind of solving some equations here, and kind of based off the way that I have kind of taught. So when we're identifying the LCD, we're looking for factors that they have in common. Really, y plus 1 and 3 do not have any factors in common, so I am just going to multiply by my LCD on both sides. Okay, by doing that, you can see that my y plus 1s divide out, leave me with a 3y, and here my 3's divide out, leave me with a 2 times y plus 1. And obviously, as you get a little bit more familiar with this, you can distribute that 2y plus 2. And then let's get the y's to the same side, and we get y is equal to 2. And obviously, you can now go back to your original equation and say, yeah, that makes sense, that works. For the next example, you could say, well, I don't really feel like multiplying these 2 denominators. That kind of looks a little crazy, doesn't it? And that's true. It is a little crazy. So first thing we want to do is factor them. So if I have x minus 1 times x plus 1, and then over here I need to have, let's see, that's going to be x plus 2 times x minus 1. So here they do have a factor in common, which is the LCD, which is x minus 1. And then the factors they don't have in common is going to be x plus 2, or x plus 1, I'm sorry, and x plus 2. Okay, so now we have an LCD of 3 terms. Now, again, you can do it just like this one, but you can see like this is a lot of writing, right? So after this, I'm going to give you a little bit of another way to do this that's a little bit easier that you can understand. And obviously, once you kind of work through a lot of these examples, there's some other shortcuts that hopefully you'll kind of identify as we keep on doing more and more of these that will make your life a little bit easier. But first of all, we see that when doing this, the x minus 1s divide out, the x plus 1s divide out. Just leave me with a x plus 2. And then on the right side, my x plus 2s divide out, my x minus 1s divide out. Leave me with a 2 times x plus 1. Well, now, again, I can go ahead and distribute. Okay, and then let's just get the x's to the same side. And therefore, you get x is going to equal 0. Now, some of you might have already been saying, you already recognize this and say, oh, do the cross product, cross multiplication, and yes, that actually works as well. I don't teach it, I allow it. I don't teach it to my students just because from my experience, what I noticed, in a chapter like this, where we're multiplying, dividing rational expressions, as well as solving with multiple fractions, people misuse cross multiplication all the time. You can only apply the cross product when you have a proportion, basically a fraction equal to a fraction. And these are the only 2 problems that we're going to do in this lesson where you could have applied the cross product. And basically what the cross product allows us to do is just multiply directly across. Again, we have a fraction equal to another fraction. So if I go ahead and apply the cross product, then I'm going to have 2x squared minus 1 is equal to x squared plus x minus 2. Now, again, you could also have a good debate as far as saying, I'm not sure if that is actually easier now than if it was just to multiply by the LCD. Sometimes the cross product is, like over here, if you were to apply the cross product, you would get 2 times y plus 1 over, equals 3y, which is exactly the same process that we just had. Right now, obviously, I showed a lot of work because I'm teaching, but you could do this exact same stuff multiplying by the LCDs and not show as much work to me. But it's important for us to kind of see the difference here, at least in this problem, as far as what happens when we find the cross product. Because in the first example, applying the cross product to LCD is not going to make a difference. But here, I'm actually going to get a different answer, which is kind of interesting here. X squared, I'm just going to have to subtract an x, and I'll have to add a 2 to both sides. So by doing that, I get 2x squared minus x equals 0. Factor out the x, and I get x minus 1, x times x minus 1 equals 0, so I have x equals 0 and x equals positive 1. So this is weird. By applying the cross product, I have now 2 solutions, whereas the original equation, I only have 1 solution. So, what is the correct one? Which one is, which one should we use? Well, the important thing is we recognize if we were to take 1 and plug it back into the equation, we recognize that that is an extraneous solution. So in this case, we don't need to label any of our extraneous solutions. We only had 1 solution and it worked, so we are good. Whereas this case, if we solve by this method, we have to make sure that not only we have to solve for 2 solutions, but we have to recognize that the x equals 1 is also an extraneous solution. So we'd have to label it as such. So that's kind of how those problems can differentiate there that you want to make sure that you're aware of. So, if you prefer cross multiplication at all times, go for it. I think though, multiplying by the LCD and not showing as much step-by-step work can be just as fast as well as easy as cross multiplication. And again, the other major thing that I see students do is they misuse it. They cross multiply right here. And I'm like, no, that's the reason why I don't say cross multiplication. That's the reason why I don't teach cross multiplication. Cross multiplication is only when you have a fraction. So let's do it like this. When you have a fraction equal to another fraction, okay, which we call a proportion. Therefore, A times D is equal to B times C. So, I mean, it's perfectly fine, but just don't use it when you have more than, when you don't have fractions adding or subtracting or multiplying and dividing, or you have like, 3 or 4 fractions. Don't be trying to do anything crazy. All right. In the next example here, you could just multiply by the LCD, which would be my preferred method. However, we do recognize like these both have the same denominator, right? So couldn't you just put them under like x minus 1 equal to 4, right? Is there anything like wrong with just combining numerators here? And then you just multiply by x minus 1 on both sides. Therefore, you'd have 2 plus x equals 4 times x minus 1. Now, in my preferred terms, I'm just going to say the LCD is x minus 1. So if I multiply everything times x minus 1, the x minus 1's divide out, leave me with a 2. Here, the x minus 1's divide out, leave me with an x, equals 4 times x minus 1. So you can see, like, it's the same idea. Like, there wasn't one that would have been easier. I mean, maybe easier than the other, but you're going to get to the exact same equation. So now let's just go ahead and distribute here. So I'll just solve this one just to kind of choose for x minus 4. And then let's get the x's to the same side and get the numbers to the same side. So the 6 equals 3x, divide by 3, flip it over, and we get x is equal to 2. Plug that back in, and we can see that that is not extraneous, so we're all good. And next example, we only have one denominator, and it's a variable x. So I'm just going to multiply everything times x. And again, it's very important to make sure we multiply everything times x. Because, that is going to produce what we call an equivalent equation. Okay, so now I recognize I have a quadratic. It's not in standard form though, so I'm just going to rewrite it in standard form. And now I say, okay, so now I can either factor this, quadratic formula, complete the square, and I say, all right, what two numbers multiply to give me 12, add to give me -8, and I'm thinking 6 and 2, -6 and -2. Therefore, we can say x equals 6 and x equals 2. All right, so on to the next example. So now we have a couple more fractions here. But again, like the same idea here. Again, we don't want to just multiply. We see that these are the same. So a couple different ways we could do this one. If you love cross multiplication, then obviously you could go ahead and say, well, why don't I just add the 2 over x plus 2 to the other side? So therefore, you would have, 3x over x squared minus 4 equals, let's see, add a 2, so that's going to be a 3 over an x plus 2. However, if you were to do it this way, I will let you know that you are going to get some different solutions than if you just multiply by the LCD. So again, it's just making sure that you understand your solutions or your process here. You can apply the cross product if you like, right? However, my idea, guys, is to understand, well, what do these have anything in common? By factoring these, I see this is x minus 2, x plus 2, right? I'm actually just going to delete that. I did have some students went and do that. They love cross multiplying, so I'm like, that's fine. Just make sure that you're going to get the same answer, obviously, as me. And as long as you're applying cross multiplication, okay, or in the right context, and then I'm fine with it. But you recognize now the LCD, what they have in common is x minus 2. I'm sorry, x plus 2. What they don't have in common is an x minus 2. So therefore, I'm just going to list that as x plus 2 times x minus 2. So again, multiply everything times this LCD. And you could write it as a product of each and every one of those, but obviously to save myself some time, I am not going to do that. So, we just multiply these. You can see, though, that whatever's in the numerator is in the denominator. That's why I don't have a denominator anymore, right? It got divided into it. Whereas here, only my x plus 2 can divide into that. So therefore, that's going to leave me with an x minus 2. Be very careful to keep check with that negative. So that becomes a -2 times x minus 2, right? Because the x plus 2 is divided out. Here again, the x plus 2 is divided out, so I'm left with a 1 times x minus 2. I don't need to be as careful with a 1 as far as my distributive property, but it's very common for students to make a mistake here with that -2. All right, so now we can go ahead and distribute. And then we just need to get the x's to the same side. And we get something very interesting. 4 is equal to -2. Well, that's kind of weird. Again, we're trying to find solutions, and then we get a statement that is not true. So what does that mean in the context of the problem? That means there's no solution. And if you were to have done that original equation or the original problem, you only would have gotten one solution, and it would have been extraneous. So therefore, that's another way for you to receive no solution. So that was kind of important here about that question E. That was a way for another way. If you see the cross multiplication, if it would have been easier, you still would have gotten no solution. You would have got one solution, but it would have been extraneous. In the next example, hopefully you guys can recognize that my LCD here is going to be x minus 1 times x plus 1. So multiply everything times that. And by multiplying everything times my LCD, I just have to write it out there. My x minus 1's divide out, so let's leave me with 2 times parentheses x plus 1 equals, now 1 times x minus 1, x plus 1, let's actually, multiply that out, right? Like what is x minus 1, x plus 1? That's x squared minus 1. So typically I don't really, we like the things in factored form, but obviously if you're multiplying by this number, let's use that simplified value. So x squared minus 1. And then minus, here we're going to have x plus 1's divide out, so it's going to leave me with an x minus 1. Again, being very careful with that negative and parentheses. Okay, let's use distributive property here. 2x plus 2 equals x squared minus 1 minus x plus 1. Let's subtract the 2x to both sides. Let's subtract the 2 to both sides. So I get 0 equals x squared minus 3x. And then let's see, that becomes a negative, what's a minus 2? Is this a problem? I kind of forgot about this example. Yeah, that is the answer. Okay, so that becomes a negative 1, or that becomes 0 minus 2. Okay, so now we say, all right, let's go ahead and factor, right? And then we recognize and we say, crap, this is not factorable. There are not any two numbers, at least real integers, or rational numbers that multiply to give you negative 2 and add to give you negative 3. So therefore, when we have a quadratic set equal to 0, we can now use the quadratic formula. So in this example, what I'm going to do is I'm going to have x equals opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that becomes 3 plus or minus. Let's do some math in our head here. Negative 3, that's squared. Negative 4 times negative 2 is a positive 8. 9 plus 8 is 17. Divided by 2. And obviously, obviously it's pretty obvious to note that neither of those answers, when you plug them in, is going to make my denominator 0, because the only numbers that make my denominator 0 are going to be 1 and negative 1. So therefore, that's neither of those. Those are your solutions, which are irrational. Perfectly fine. Just make sure you can apply the quadratic formula if it is non-factorable. All right, so let's kind of continue on. So you can see this one's kind of same here. But again, this is another factored form, n minus 1 times n plus 1. So multiply everything. Okay, and what we get is we like the ones here. We don't have to worry about distributive property. Here we get a 2n equals 2. Divide by 2, n is equal to 1. And again, we recognize when we plug in 1, that gives us, when we plug in 1, that gives an extraneous solution, right? So since we now have an extraneous solution, this is another example of no solution. So we can get a no solution here from, getting a statement that is incorrect. Or actually, if we go ahead and solve and we only get one solution, but that one solution ends up being extraneous, therefore then it's going to be no solution. For the next one, we see a trinomial as my denominator. So let's go ahead and factor that here to n. Let's see, that's going to be a negative 8. So that'd be n plus 4 times n minus 2. Now, I had a little trouble factoring this, right? I kind of thought about that for a second. But the important thing is, I have two other factors, or two other denominators here. It's not always the case, guys, but it's a good tip to look at these other two denominators, right? Because when you're trying to identify the LCD, and you saw in that second example, if you have three factors, if this was factored not including these two numbers, you would have four 4 factors in your LCD. That's going to create a very complicated problem. Even 3 factors in your LCD is going to produce a large problem. So it's not always a guarantee that, you know, the factored form of this quadratic is going to be these 2 denominators. But the more factors you have in your LCD, the more complicated the problem is. So if you have something you need to factor, I would definitely look at those other 2 denominators, because they're either both going to be the factored form of that, or at least one of them is going to be have some shared factors in that case. So, because otherwise the problems are just going to get so big, it's just not going to be, you know, worth it to like be doing the math on it, because it'll just take so much time and so much algebra to go through. All right, so here's my LCD. Multiply this by every term. So you can see the n minus 1s are going to divide out. Here you can see my n plus 4 and my n minus 1s would divide out, 2n plus 1. Plus here you can see my n plus 4s divide out, so that'll leave me with a 2 times n minus 2. But don't write it like this, right? Because you want to make sure you use the parentheses. And that's just a very big mistake. People write it like that, and then they'll have it as 2n. And they'll have 2n minus 2, but it's not 2n minus 2. It's 2n minus 4, because you have to apply distributive property. All right, so let's subtract the 1 here, and then let's combine like terms. So I have 0 equals 4n minus 3. Add the 3. 3 equals 4n. Divide by 4. Divide by 4. N equals 3/4. Okay. And yep, there you go. One solution. Just make sure it checks, verifies, all good. All right, we're almost done, guys. We're just keep on working on through there. You can see a lot of the same thing over and over. Like my main goal is just get rid of these fractions, simplify, you know, and simplify and solve, and then make sure that I understand the solution in its context of the problem. So here I recognize another difference of 2 squares. I'm going to multiply everything times that LCD. Oh, this is n, right? Sorry. Did I do that up there? No, I didn't, but that's okay. Yeah, that's what I'm just gonna move that over to save myself some time. All right, so when I multiply it here by this first term, you can see my n minus 3, my n plus 3s divide out. So that's just going to leave me with the 4n squared, minus my n plus 3s divide out, leave me with a negative 2n times n minus 3, equal my n minus 3s divide out here, leave me with a 3 times n plus 3. And again, don't write it like that, use parentheses. All right, so let's go ahead and do some distributive property. 4n minus 2n squared plus 6n equals 3n plus 9. Let's get the 3n to the other side. Let's get the negative 9 to the other side. So I get a negative 2n squared. That becomes a 3, so that becomes a positive 7n minus 9 equals 0. Now again, if I was going to factor this, I don't want that negative in front, right? But I do want that negative. How do I get the negative 9? I don't remember this being the problem. Let me just double check and make sure I did my correct. What happened to the 4n squared? Ah, that's where I made a mistake. I forgot to put the square there. Because I was like, I remember doing this problem. I don't remember having that as the example. So 4n squared minus 2n squared is a positive 2n squared. That becomes a plus a 3n minus 9 equals 0. Okay, so now we got to see, is this factorable, right? So we know that this is a quadratic triangle. So since it's a quadratic, we know that it can be factored into a product of 2 binomials. And I know those coefficients here are going to be 2n as well as n. And we want to multiply to give us negative 9, but we were looking for a difference of our products to give us 3n. So I'm automatically thinking of positive 3 and negative 3, right? And again, if you multiply this out, just kind of doing this in your head, you can see that this works. So therefore, I use the zero product property to set them both equal to 0. And then I can see n equals 3/2, and n is equal to -3. So, therefore, now let's go and check our solutions, make sure that they both work. And however, when I plug -3 back into this equation, you can see it's going to make this fraction 0. So therefore, that is extraneous. And there's only one solution, positive 3/2. For the next example here, in this next example, again, we want to see, well, I think this factored form might be like this, right? So x plus 2 times x plus 3. And again, that does work. So therefore, I'm going to multiply everything times x plus 2 times x plus 3. And by doing that, I get 3 plus x minus 1 times x plus 3 equals 7. X plus 3 is divided out, leave me with an x plus 2. Okay, so now in this case, I need to go ahead and use FOIL, right? Multiply these out. So that's going to give me 3 plus, when you multiply that out, they give you x squared. I'll just do it out. That gives me a negative x plus 3x minus 3 equals here, distributive property, 7x plus 14. Now let's just go ahead and combine like terms here. So let's see, those are going to add to 0. So left with x squared plus 2x equals 7x plus 14. Let's subtract those on both sides. 14. So that's going to leave me with an x squared. Let's see, minus 5x minus 14 equals 0. And again, now we want to make sure that we can see this to be factorable. And I see that, yeah, I can do this as x minus 7 times x plus 2 equals 0. So therefore, x is equal to 7 using the 0 product property, and x equals -2. However, when you take x equals -2, you plug it back into the original equation, you see it does not satisfy that. So therefore, x equals -2 is an extraneous solution. So that's basically what we did, ladies and gentlemen. I covered a lot of different examples for you to be able to how to solve your rational expressions. And you can see it's basically the same thing over and over and over again. I really like to multiply by that LCD to get rid of the fraction, because I think that just makes all these problems really kind of basic and easy for you to go ahead and solve. However, that process that we did for that is also the same process that I want to remind you of what we covered in the first unit, which was complex fractions. So when I first taught complex fractions to my students, it was kind of at the end of class. We already had added, subtracted, multiplied, divided, and students were kind of a little fatigued. And even though I taught it to them, I know complex fractions is probably something that they do not have a lot of experience with, and they really need a lot of practice to go ahead and simplify. So what I decided to do was to teach it again, kind of like reteach it, or at least just give them more practice on this, because really complex fractions is related in terms of operations with the add, subtract, multiply, divide, and simplify that we did in the first day of this lesson. But it's also very similar to this lesson because the steps, the process that we're doing is exactly the same. We are multiplying by the LCD to eliminate our fractions, right? So when I multiply by x minus 1, I eliminate my denominators, x minus 2 or x minus 1. When I multiply by x minus 2, I divide out my denominators. So therefore, I only have one big fraction. Whereas here, when I multiply everything times x plus 3 times x plus 4, I get rid of all my fractions. I get rid of all those little fractions because they all divide into their terms. And then I can just go ahead and simplify. The only thing that we didn't talk about in day 1, which I wanted to bring up to my students today because we have a little bit more time on this, is understanding the restricted values based on the fraction. And not only do the denominators here, when we know that x cannot equal 2, but understanding the restricted value in the denominator. So here you can see this is 3x minus 7. So therefore we got to set that equal to 0 and solve. And obviously that's going to give us a value of 7/3. So x also cannot be 7/3. So it's not just the original problem for excluded values. You also want to look at the final simplified problem for your excluded values. All right, so I'm just going to cover 4 more examples. Yeah, so just 4 examples of just practicing this. So therefore students can feel more comfortable. So we're going to simplify as well as identify or label the excluded values. All right, so the first one here is I recognize my LCD is just the product of my denominators, which is a 3x, right? The 3 and the x don't have any factors in common, so I'm just going to multiply everything by 3x. And when doing that, I get 3 plus x over 3, no, x minus 3. And you can see how everything, 3x times 1/3 is just going to give us x. 3x times negative 1 over x is just going to give us a negative 3. Now, obviously, we know that as far as excluded values go, in the original problem, x cannot equal 0. In my simplified problem here, I know that x cannot equal 3. So you can see how that simplified problem actually produces an additional excluded value. I factor this here just to make sure that it is the same, which it is. So therefore, my LCD that I'm going to multiply everything by is going to be x minus 1 times x plus 1. Okay, so I multiply that by the first fraction. The x plus 1's divide out, leave me with 2 times x minus 1. Here, my x minus 1's divide out. That's going to give me, oops, what is that, a plus? Plus x times x plus 1. And then over here, those terms divide out, just leave me with a 3x. So now let's go ahead and simplify that using distributive property. So I get a 4x minus 2 plus a x squared plus x all over 3x. And then I could just, rearrange this one more time. X squared, those combine to give me a 5x minus 2 over 3x. Now again, going back to my original problem, we know that x cannot equal negative 1 and positive 1, so I'll just do plus or minus 1, as well as 0. All right, next example. You can see here, this is kind of interesting. These we have like every single thing is different. But if I factor this, then that's going to give me an x times a x plus 2. So it has an x in common here, and it has an x plus 2 in common here. So therefore, my LCD is going to be x times x plus 2. And again, this would be 1, right? So the fraction. So if I multiply x times x plus 1 times our first term, well, that denominator is going to divide into that. So that's just going to be with a 1. Minus here, my x's will divide out. So I'll be left with a 2 times x plus 2. Here, my x plus 2's divide out, leave me with a 3x squared. And then here, nothing divides out, so that's going to leave me with a negative 2 times x times an x plus 2. Okay, so now let's go ahead and see how everything simplifies. So I get a 1 minus 2x minus 4 all over a 3x squared minus a 2x squared. And that'd be a minus a 4x. Right? Because you got to make sure you apply distributive property there. And you're multiplying the negative 2 and the x. So let's simplify that one more time here. So that gives me a negative 2x minus 3 all over 3x squared minus 2x squared. It's just going to give me an x squared minus 4x. Now, again, factoring that, or setting that equal to 0, you get an x times x minus 4 is equal to 0. So x equals 0 and x equals 4. All right, so looking at my restricted values, I know x cannot equal 0, right? I know it cannot equal negative 2. This is just a combination, this is just a combination of those two factors. So the only thing added now is going to be a positive 4. But you can see we have 3 restricted values. All right, last example here. Very, very similar common denominator. In this one, though, we can see if we do our math, we factor this, then it's kind of like this exact same type of problem. We're going to have x times x minus 1. All right, so when I multiply that times my first term, my x's divide out, leave me with a x minus 1. Here, my x minus 1's divide out. So that's going to leave me with a minus, I'm going to use parentheses, x plus 1 times x. Now, you could put the x in front if you wanted to. That might be a little bit easier. Let's actually do that. It's just going to be easier to distribute that way. All over here, my x minus 1's divide out, leave me with a 3x squared. And then here, everything divides out, leave me with a positive 1. All right. combine some like terms here. I get x minus 1 minus x squared minus x. That goes to 0, so I'm left with a negative. Oops, sorry. Should probably... now let's rearrange the terms. That goes to 0, so that's a negative x squared minus 1. Here we have a 3x squared plus 1. Now, you could, there's really nothing else that we can really do to simplify this. So let's look at our excluded values here. We know x from the original problem cannot equal 0 and x cannot equal 1. But then we want to set this denominator equal 0 like we did over here, right? But something interesting here again happens. When I set 3x squared plus 1 equals 0, well, I get a 3x squared, equals a negative 1/3. Well, now if I want to go ahead and take the square root of that, well, that's going to be in my complex number system. So I don't need to exclude complex numbers. I only need to exclude real numbers that make my denominator equal to 0. So hopefully that helps you guys out as far as, now that we looked at complex numbers or complex fractions first in the first lesson with, operations and simplifying, to now looking at complex fractions in the last lesson with solving, where we multiply by the LCD. And that's really, where it kind of comes down to for solving these is simplifying these expressions. So therefore you don't have as many fractions. And, from the beginning of this lesson, when you eliminate as many fractions as possible, you're making your life a lot easier. But it is important to make sure that we still understand our excluded values, especially when we are solving, because when we're solving and we have a solution that is an excluded value, it is an extraneous solution and actually not a real solution to the equation. So there you go, ladies and gentlemen. That is the last section in rational expressions. I hope you guys enjoyed, and I look forward to seeing you guys in the next video.